Electric vehicles are revolutionizing the automobile industry as we speak. From two-wheelers to cars, and even buses to aircrafts, EVs are the inevitable future of transportation. By 2025, it is estimated that about 20% of all new cars sold worldwide will be electric. And by 2030, this number is expected to rise to 40%. Although they are taking over the market right now, there were times in history when EVs were the preferred mode of transportation, but lost out to conventional internal combustion engines, or IC engine cars, for their poor range and heightened costs. So let's take a step back and look at the evolution of the EV and how it came to be. Going back a few centuries, it all started in 1828 when Ányos Jedlik developed a small electric car with an electric motor. Even though his model was nothing like the EVs we have today, it definitely set the foundation for future innovations. Moving on to the 1830s, Thomas Davenport experimented with a DC electric motor and invented a locomotive to run on an electrified track. But it was not until later on in the decade that focus shifted to batteries, when Professor Sybrandas Strating of Groningen developed a small-scale electrical car operating on non-rechargeable batteries. In addition to this, Robert Davidson built an electric locomotive that worked on batteries. Only about 20 years later, in 1859, did rechargeable batteries come into play after the invention of the lead-acid battery by Gaston Plante. Picking up where Plante left off, Camille Foix improved battery capacity, which initiated the manufacturing of batteries on a larger scale. Towards the end of the 19th century, William Morrison developed a functional EV. During this period, many car manufacturers began dabbling in the field of EVs as it appealed to them for having overcome limitations of the IC engine car, like unpleasant sounds, smells, and vibrations, as well as the hand-cranking mechanism. It is these very limitations that drove the IC car to make strides in development. And this did not take long, as the launch of the Model T by Henry Ford in the beginning of the 20th century brought the hype over EVs to a grinding halt. The mass production of these gasoline-powered cars outshined the EVs, with increased ranges, easy availability of fuel, overall affordable pricing, and the introduction of an electrical starter that no longer needed manual hand cranking. As the ownership of EVs exponentially decreased, gasoline-powered cars reigned for the next 30 years. But all good things must come to an end. And this is exactly what happened in the 1970s when the oil crisis came in like a wrecking ball. Fuel costs rocketed and concerns about pollution filled the air. Although these concerns put the spotlight back on EVs, the gasoline-powered cars were so popular by then that it would take a good decade or two for the EV to emerge again. Fast forward a few years to the 1990s when GM released the EV1 and Toyota released the Prius. Nearly a decade later, Tesla released its Roadster in 2008, the first EV with the ability to travel greater than 320 kilometers on a single charge. And this is when the EV made a strong comeback. Car manufacturers started focusing on EVs more than ever, with releases like the Nissan Leaf and the Chevrolet Volt taking center stage. The rule of EVs was intensified by the plummeting cost of EV batteries by 50% in 2010. With EVs like the Tesla Model S in 2012 and Model 3 in 2017, EV sales continued to soar. Luxury car manufacturer Porsche released the Panamera SE Hybrid for 2013. In 2014, BMW released the BMW i3 and i8 in 2014. A few years later, in 2018, Jaguar released the I-Pace. The increasing sales of EVs was clearly demonstrated in 2021 when the worldwide sales of the Tesla Model 3 crossed a whopping 1 million units. Now, if this isn't what you call in demand, I don't know what is. The development of EVs over time has led us to 3 different types now available in the market: the battery EV, the hybrid EV, and the plug-in hybrid EV. All of these run on varying extents of electricity. Battery EVs have rechargeable batteries and are solely powered by electricity. Since they do not emit greenhouse gases, they are not equipped with a tailpipe. On the other hand, plug-in hybrid EVs run on electricity and gasoline and have the ability to shift between the two as needed. Within their mechanism is a battery to drive the electric motor and a fuel tank to fill gasoline and run an IC engine. So in the case that the battery runs out of charge, you can continue to drive on just fuel, and vice versa. Similar to these, hybrid vehicles are also powered by gasoline and electricity. But unlike the plug-in hybrid EV, the battery cannot be charged directly. Instead, the battery gets charged through a mechanism called regenerative braking, as well as by the IC engine. In both plug-in hybrid EV and hybrid EV, the battery and IC engine work together to maximize performance, bring down fuel economy, and reduce CO2 emissions. And as you can see, the electric vehicle has been through quite a ride. But the ride is just getting started, so stay with us to find out more. Behind the working of an EV are three main parts connected together: the battery, controller, and motor. As it is an electric vehicle, all these parts have electricity flowing through them, unlike their IC engine counterparts. And just like any other electrical or electronic device, EVs need a source of power. For the EV, this happens to be an EV charging station. But forget cars for a second. What do you do when any of your smart devices are about to run out of juice? Probably plug in the charger to charge the battery, right? Well, the same goes for EVs too. EV charging stations can be likened to the USB charging stations for mobile phones available at airports. If your battery is running low at the airport and you don't have your charger on you, you find a charging station to charge your device. EVs can either be charged at commercial charging stations or at the one you have installed at home. Before we continue, let's recap alternating and direct current, or AC-DC. In DC, the electrons travel in one direction, but in AC, the electrons regularly change direction and move back and forth. So if we look at this on a graph, DC would be a straight line, and AC would be a sinusoidal wave that shifts between positive and negative phases. EVs receive alternating current from charging stations the same way our household appliances are powered. And as with any device, electricity has to be converted from AC to DC before it can be stored and used. In the EV, this conversion is taken care of by the onboard charger. Smaller EVs like scooters have off-board chargers. Similar to your mobile phone and laptop, EVs also use a lithium-ion battery pack for its rechargeable edge. But unlike your device that has only one lithium-ion battery, EVs have more than hundreds of lithium-ion batteries packed together under the hood. For EVs, these battery packs boost overall efficiency and offer high energy density, power-to-weight ratio, and temperature performance. In other words, the lithium-ion battery stores an ample amount of energy for its weight. All these put together allow the car to travel greater ranges on one charge. When your battery is charged and you are ready to get going again, you turn the vehicle on and press the accelerator pedal. Now the cool thing here is that depending on how hard you press down on the pedal, the amount of electricity sent to the motor controller varies. So the faster you go, the more electricity is consumed. Okay, let's back up a bit. So if you remember, power from the grid is AC and gets converted to DC for storage in the battery. Before it can be fed to the motor, it needs to be converted to AC again. And once this is done, the AC is fed to the electric traction motor, which then rotates the axles. It is here that the electrical energy is converted to mechanical energy that drives the wheels forward. EVs may have AC or DC motors depending on their application. Larger vehicles are more likely to have AC motors, while smaller vehicles tend to have DC motors. The type of motor used also varies across car manufacturers and models. For instance, Tesla produced the Model S with an AC motor, and the Model 3 with a DC motor. Charging stations are not the only means of charging your battery. When you hit the brakes in an EV, not only does the car stop, the regenerative braking system kicks in. This charges the battery by converting kinetic energy from the rotation of the wheels to electrical energy needed to charge the battery. So, when you're moving, the motor focuses on rotating the wheels, and when you press the brakes, it shifts its focus to restoring energy in the battery. But at times, all the kinetic energy may not get converted into electrical energy because the battery may be completely charged. With all of these parts working together, there is obviously going to be a lot of heat generated. Oftentimes, the battery, motor, and controller may overheat due to peak loads of current and outside temperatures. And this is why a battery thermal management system is in place to ensure optimal temperature is maintained for proper functioning. A glycol coolant flows through the pumps inside the circuitry, absorbs heat, and releases it into the atmosphere. As the coolant has high specific thermal capacity, it is able to absorb heat in a small space. When all's said and done, the EV is an efficient machine that is more than just about saving the environment. The modern electric vehicle is about to buy out the conventional IC engine car. So much so that roads may be fully electric in a decade or two. Although the IC engine car and EV look similar on the outside, their inner workings are anything but the same. And it is these very differences that this video is here to take you through. It all starts with their source of energy. When driving an IC engine car, you would pull up to a gas station to fill petrol or diesel. But for an EV, you would have to stop at a charging station to charge the lithium-ion battery pack with electricity. As the name suggests, for an internal combustion engine car to run, combustion has to take place. And with any internal combustion system is the release of greenhouse gases and noise pollution. On the other hand, EVs are powered by a battery pack and electricity, because of which there is minimal greenhouse gas emission and noise pollution. Even though hybrid and plug-in hybrid EVs are partially powered by fuel, the overall CO2 emission of these is relatively less than that of an IC engine car, which is fully powered by gasoline. Now, hold on. We can't ignore the elephant in the room. Yes, EVs indirectly emit greenhouse gases because the electricity they run on is generated from burning fossil fuels. But at the same time, this amount of CO2 emission does not come close to that released by IC engine cars. Although this difference in energy source sounds like it gives the EVs an edge over the IC engine car, it does come at a cost. While the IC engine car can be filled with fuel in less than 5 minutes, the EV takes an hour or more to fully charge. And in our fast-paced world, the EV definitely takes a hit on this one. The high energy density of fuel in IC engine cars also overshadows the energy density of lithium-ion battery packs. These batteries are packed together and evenly distributed on the floor of the vehicle. Because of this design, the EV's center of gravity is lower than that of an ordinary car's. This in turn provides reinforced stability during collisions and makes the EV a tad safer. However, the regular charging and discharging of these batteries generates a lot of heat, which, if not controlled, can interfere with the operation and safety of the EV. To prevent overheating, a battery thermal management system is in place to ensure optimal temperature and remove excess heat via the radiator. Their IC engine counterparts, instead, have a cooling mechanism to manage the heat of their engine. This difference in heat generation can be attributed to their distinct working principles. In IC engine cars, combustion gives rise to the temperature and pressure needed to move the pistons. This transmission translates to the drive wheel, which in turn turns the tires. All of this mechanical action often causes uneven force and power. But in an EV, the motors turn the drive wheel by a simple three-phase AC input. As the AC power input gets linearly scaled and fed to the motor, the speed and power output is uniform. This also means they have more torque right off the bat when compared to the IC engine car. These conventional vehicles also have a complex transmission system, which means that they require gear shifts to function across different ranges of speed. However, EVs have a single-speed transmission that allows them to work across different ranges of speed. This is because the speed at which you travel is determined by the extent to which the accelerator pedal is pressed. When you take your foot off the accelerator pedal and press the brake, the kinetic energy is transformed into electricity that the battery can then store as charge. But for the IC engine car to be able to do this, it needs a battery and brushless DC motor. And if it isn't obvious by now, the IC engine car has way more moving parts than an EV. As the EV has less parts and just one moving part, which is the motor, maintenance costs are significantly lower. Regardless of EVs coming with a hefty price tag at the time of purchase, they are actually a third cheaper than the IC engine when considering maintenance and travel per mile costs. Now that we have covered the basic differences between EVs and the IC engine car, let's take a look at the pros and cons of EVs. A few advantages of the EV are that they do not require gasoline, and as a result, have minimal CO2 emissions. They are also cost-effective in the long run, easy to drive, and reduce noise pollution. Although minimal noise is supposed to be a good thing, silently moving around on the road may be a safety hazard. On a similar note, let's look at the cons of EVs. And as good as they sound, they do have a few. EVs may not have a strong presence in countries with poor electricity sources, as their usage may hinder electricity needed for daily life essentials. Charging points are also not as easily accessible or available at this point in time. And even when you find one, charging an EV takes more time than filling gas in an IC engine car. And unfortunately, EVs cannot be fully deemed eco-friendly, as their source of electricity may be generated from non-renewable fossil fuels. When deciding whether or not to buy an EV, it may appear to be a luxury investment for many due to the initial price tag. Now, here's our question. Which vehicle would you buy? We'll let you sleep on that for now. Electric vehicles are supposedly powered by electricity, right? They are electric vehicles after all. But what if we told you that some EVs are partially powered by an IC engine? While battery EVs are fully electric, there are two other partially powered by an IC engine: the hybrid EV and the plug-in hybrid EV. Each type of electric vehicle has its own set of features that appeal to consumers and give them the flexibility to choose which is best suited for them. Here's a look at how each type of EV works. Battery EVs are all electric and solely run on electrical energy from a battery pack. As these EVs do not have an IC engine, drivers do not need to stop at gas stations. Instead, you would have to stop at charging stations to charge the battery pack by plugging it into an external power source. When you're ready to go, pressing on the accelerator will signal the motor to rotate, which in turn makes the wheels go round. Battery EVs, being all electric, have minimal reciprocating parts that reduce their overall cost of maintenance. A few battery EVs you may have come across are the Tesla Model 3, Chevy Bolt, and the Nissan Leaf. Unlike the battery EV that just has a battery pack, hybrid EVs have an electric motor and an IC engine. While the electric motor runs on the battery pack, the IC engine runs on fuel. Both the IC engine and the electric motor work together to propel the car forward. Even though the hybrid EV has a battery pack, it can't be charged by plugging into an external power source at the charging station. So, how would you charge the battery of a hybrid EV if it runs out of charge? Well, this is where the IC engine steps in. Hybrid EVs can charge their battery pack with the IC engine or by means of regenerative braking. There are two further types of hybrid EVs, the fully hybrid and the mild hybrid EVs. Fully hybrid EVs can operate on just the electric motor, IC engine, or a combination of both. The mild hybrid EV, on the other hand, can only operate when the IC engine and electric motor work together. However, the motor can only help out during acceleration because it has a lower power rating than the engine. Common models of hybrid EVs are the Toyota Prius, Toyota Camry Hybrid, and the Honda Civic Hybrid. Similar to hybrid EVs are the plug-in hybrid EVs, which also have an IC engine and electric motor responsible for propulsion. But unlike hybrid EVs, the battery pack of plug-in hybrids can be charged at a charging station, and the fuel tank can be filled at a fuel station. This gives drivers the flexibility of choosing between a charging or fuel station when on the go. So, the battery pack of a plug-in hybrid EV can be charged with an external power source, by the IC engine, or regenerative braking. The cool thing about plug-in hybrid EVs is that they can run on two modes, an all-electric mode and a hybrid mode. In the all-electric mode, the EV is fully powered by the battery pack, and in the hybrid mode, it can be powered by both fuel and battery pack. So, if you drive a plug-in hybrid EV, it generally starts out as all-electric, but changes to the hybrid mode depending on speed and range of travel. It also switches between these modes depending on the charge or fuel available. If the battery runs out of charge, the IC engine will take over and vice versa. These EVs have a smaller IC engine and larger battery pack when compared to the hybrid EV because the electric motor is the prime source of propulsion. This allows plug-in hybrids to run for longer ranges and is preferred by consumers for this very reason. The Chevy Volt, Porsche Cayenne SE Hybrid, and Mercedes S550e are a few plug-in hybrid EV models. When set against the IC engine car, hybrid and plug-in hybrid EVs bring more fuel economy, less greenhouse gas emissions, and fuel costs to the table, all of which, when put together, reduce the carbon footprint of the EV. Electric vehicles are the confluence of many components working together. Each of these components must individually function efficiently to optimize EV performance, which is measured in terms of vehicle efficiency. In IC engine cars, this is measured in terms of the distance a vehicle is able to travel per liter of fuel. Vehicle efficiency also focuses on reducing greenhouse gas emissions and fuel consumption. But as EVs do not use fuel, their efficiency is measured by distance per unit of charge. Modifying an EV to maximize performance and efficiency is basically what optimization is. This can also be achieved through reducing their weight and drag. Let's start with vehicle weight. The weight of a vehicle influences the amount of fuel or charge it consumes. Here's a quick look at how this works. A heavy car like an SUV weighs more than a small city car, so it would take the SUV more fuel to move 1 kilometer than it would take the smaller city car to move the same distance. And the same applies for EVs. The heavier the car, the more charge it needs for propulsion. In fact, by reducing the weight of a vehicle, it will have an improved horsepower to weight ratio that will enhance handling, acceleration, and lower braking time. Efficiency in terms of weight reduction for EVs boils down to having lightweight cars with smaller battery packs that can power the vehicle to travel greater ranges. Sounds simple, right? Well, it's easier said than done because car manufacturers need to strike a fine balance between vehicle weight, energy consumption, and efficiency without affecting safety. So if we take the Tata Nexon, an IC engine car weighing 1,315 kilograms, and its electric counterpart, the Tata Nexon EV, weighing around 1,400 kilograms, we can see that the EV weighs more. And even heavier than all-electric vehicles are hybrid vehicles with weight from both the battery pack and engine. This ultimately increases the amount of energy required to propel them forward. Heavier vehicles also experience more rolling resistance, otherwise known as the force that resists forward motion. Car manufacturers have therefore started testing out different lightweight materials. While most car bodies are made from steel for their strength and durability, this actually adds a lot more weight to the car. To reduce this weight without taking a toll on the strength and durability of an EV, combinations of steel and aluminum, magnesium alloys, and advanced composites can be used instead. For this purpose, carbon fibers and fiberglass are also used in the design of bonnets. Although the weight of EV battery packs come under fire, it actually reduces their center of gravity and makes the vehicle easier to handle at higher speeds. This design also reduces imbalances during travel and provides stability when making sharp turns. IC engine cars have heavy engines located in the front, middle, or back of the vehicle, which may make handling relatively harder than the EV. And now coming to drag. The force that resists motion when an object is moving through a fluid medium. So when a car is moving through the air, drag force resists its forward motion. For instance, if we look at race cars, they have an overall sleek design with a small nose to improve their penetration through the air. Even more so, they have an aerodynamically designed windshield that reduces the resistance of the vehicle when moving forward. The vehicle also has less ground clearance, which limits the amount of air flowing below it. To keep the vehicle streamlined through the air, there are minimal to no protruding parts. And in the same way, EVs have a streamlined design with minimal protrusions to allow air to pass around its body. This is unlike an IC engine car, which have to allow air into the frame to cool down the engine. For instance, the front bumper of the Tata Nexon has air vents, whereas the Tata Nexon EV does not. This difference in design reduces the drag in the EV variant. EVs are also designed with low-drag tires that lower the loss of energy as the vehicle moves, in turn improving their range. Having fewer moving parts than the IC engine car, the EV loses less energy to friction and heat between parts, and is able to convert the majority of its electrical energy into mechanical energy that moves the car. This makes the EV far more efficient than its IC engine counterpart. Aren't EVs just the epitome of lean, mean electric machines? At the core of an electric vehicle's functioning is the electric motor that rotates the wheels. In fact, electrifying a vehicle primarily involves replacing the average IC engine with an electric motor. This makes the electric motor just as important as the battery pack that powers it. Using an electric motor actually minimizes the amount of mechanical parts and movement that goes on inside a vehicle. So when an IC engine creates traction with cylinders, pistons, and a crankshaft, all it takes in EVs is just a signal to the electric motor. But how do electric motors develop the traction needed to turn the wheels of an EV? To answer this, we need to understand what a motor is and how it works. Electric motors are machines that convert electrical energy into mechanical energy. EV manufacturers choose the ideal motor for their models by considering its efficiency, power density, acceleration, torque, and cost. They come in two main types: DC and AC motors. DC motors are powered by direct current and include brushed and brushless DC motors. AC motors are powered by alternating current and include synchronous and asynchronous motors. While the electrical energy is derived from a power source like a battery pack, the resulting mechanical energy is what gives us rotational motion. Behind this rotation is the underlying concept that when you pass a current through a rectangular coil inside a magnetic field, the coil rotates because of the forces acting on it. All magnets have a north and south pole, and while opposite poles attract each other, like poles repel each other. A magnet that naturally displays these properties is called a permanent magnet. But an average iron nail can also be made to display these properties if it is turned into an electromagnet. For instance, if we take an iron nail or rod, wrap a coil around it, and pass electricity through it by connecting a battery to it, it will turn into an electromagnet and display magnetic properties. This means that it will have a north and south pole till it stays connected to a power source. When it disconnects from the power source, it loses the magnetic properties. To understand how this fits into the context of electric motors, here's a look at the workings of a brushed DC motor. It has a cylindrical metal casing with a shaft where the drive wheels of the EV will be attached. Inside this metal casing are two main parts central to its working: a rotor that rotates and a stator that remains stationary. In this case, the rotor is the electromagnet with an armature of windings that have electricity flowing through them, and the stator is the permanent magnet surrounding the motor. There are two permanent magnets with opposite poles facing the electromagnet. By passing current through the coils, a magnetic field is developed. The polarity of the magnet depends on the direction of current flowing through it. When the north pole of the electromagnet aligns with the north pole of the permanent magnet, they repel each other, and the electromagnet moves towards the other permanent magnet with an opposite polarity. But when the north pole of the electromagnet meets the south pole of the permanent magnet, it stops rotating. Now, in order for the electromagnet to rotate again, the poles of the electromagnet and permanent magnet have to be the same. Since we're working with an electromagnet, its poles can be switched by reversing the direction of current flowing through the wires. This process of switching the polarity of electricity to keep the rotor rotating continues for as long as the battery has power to let it do so. But switching the polarity of electricity by flipping the wires each time would be a tedious task, and this is why brushed DC series motors have a commutator and brush. The endings of the coils from the rotor are each connected to a separate commutator, which is responsible for switching the polarity of electricity. Two brushes act as conductors and provide the commutator with electrical energy. So the flow of electricity in the motor would look something like this. DC series motors have a high starting torque, which makes them ideal for use as traction motors. This gives EVs with DC series motors effortless speed control and a tolerance to sudden rise in loads. But as good as they sound, they do come at a cost, that is, a high maintenance cost and low efficiency because of mechanical parts like the commutator and brush. As the brush and commutator continuously rub against each other, they wear out, generate sparks, and reduce the service life of the motor. This is why many car manufacturers prefer the brushless DC motor, commonly known as the BLDC motor, over the brushed DC motor. In the BLDC motor, the brush and commutator get replaced by an electronic system, which reduces the number of mechanical parts. This leaves us with just the rotor and stator. BLDC motors have a rotor with permanent magnets on opposite ends and a stator that is an arrangement of coils inside it. When a DC current is given to the coils of the stator, it generates a magnetic field. Here we have three different sets of coils. When coil A gets energized, it generates a magnetic field that gets attracted to the opposite pole of the permanent magnet. But right when the permanent magnet is about to get to coil A, the current to coil A is turned off and coil B is energized. This now makes the opposite pole on the permanent magnet move towards coil B. And just like with coil A, coil B will now get turned off and coil C gets energized. It is this process that repeats itself to keep the motor rotating and turning the wheels of an EV. BLDCs dominate the EV industry with their high efficiency, starting torque, and power density. They are used in the Tesla Model 3. Similar to the power density and efficiency of the BLDC motor is that of the AC permanent magnet synchronous motor. This rotation of the motor is in sync with the frequency of alternating current it receives, making it a synchronous motor. In this motor, the rotor receives a DC input and has a constant magnetic field, while the stator gets a three-phase AC input and has a revolving magnetic field. As opposite poles of the stator and rotor get attracted to each other, the magnetic field of the stator rotates while attracting the rotor. These motors are equipped with a squirrel cage surrounding the rotor to rotate at the frequency of alternating current running through the stator. In these motors, the rotor can either be a permanent magnet or an electromagnet, depending on their application. When a permanent magnet is used, this motor can function as an alternator in EVs. This means that it can be a motor that propels the vehicle and also an alternator when it comes to regenerative braking. Permanent magnet synchronous motors come with a high power rating, making them ideal for use in high-performance cars. It is because of this that car manufacturers like Chevrolet, Toyota, Nissan, and BMW use these motors in their hybrid and all-electric vehicles. While the permanent magnet synchronous motor rotates at the same speed as the frequency of current, the rotor of the induction motor rotates at a speed less than the frequency of current. This makes it an asynchronous motor. The stator receives an AC input and generates a rotating magnetic field, also known as RMF. This RMF makes the rotor, which is surrounded by a squirrel cage, rotate. In a DC motor, the power would be given to the rotor, but in this AC motor, a three-phase AC input is given to the stator. The speed at which the rotor rotates is determined by the frequency of AC fed to the stator. Because of differences in the phases of AC input, the magnetic field will have different orientations, and when these orientations are aligned, a uniformly rotating magnetic field is developed. Since the rotor rotates because of the generated RMF, there is no contact between rotor and stator. This mechanism reduces the friction and wear on the system. In order for three-phase AC induction motors to have high starting torque like the DC motors, they must undergo a series of control methods that alter the frequency. Once these changes have been made, it offers more torque for longer ranges. Tesla uses this model in its Model S and X EVs for the robust and efficient nature. At the end of the day, it all comes down to using the motor that provides maximum efficiency, torque, and propulsion for an EV. We've all heard that electric vehicles run on electric motors and battery packs. But behind the electric motor is the motor controller that manages the amount of electrical energy sent to the electric motor from the battery pack. In an IC engine car, this function is taken care of by the carburetor that manages the amount of air-fuel mixture that is let into the combustion chamber. But just as it looks, this process involves a lot of heavy gear mechanism that is avoided in EVs by just using the motor controller. Through proper coordination with the motor controller, the electric motor can produce good starting torque that gets the gear to top speeds in just a matter of seconds. Underlying this is the power converter and microcontroller. The way this works is quite similar to the human brain. When you look up motor controllers in EVs on the internet, you're bound to find them likened to the human brain. And this is because the same way the brain receives sensory input from the surroundings, the motor controller does too. A microprocessor in the EV receives signals from the brakes and throttle. These signals get processed to produce an output that controls the electricity sent to the motor with the help of a power electronic converter. This interface links the electronic components of the EVs, and its output generally manages the speed, direction, torque, and horsepower of the vehicle. Inputs coming from the battery are sent to the motor controller, which then forwards a corresponding signal to the motor. A cable connects the pedal to two potentiometers. When you press down on the pedal, it sends a corresponding signal to the controller, which determines how much power to send to the electric motor. The controller then reads the values on the potentiometers and ensures that both signals are the same. This is why there are two potentiometers for safety reasons. If the potentiometers do not have the same value, the controller will not work. Not only does the motor controller receive energy from the battery, but it also sends it back during regenerative braking. EVs use both AC and DC motors. In the case that an AC motor is used, the motor controller is also responsible for converting direct current from the battery to alternating current that can be used by the motor. Based on the type of motor used, a motor controller can be a DC-DC converter or a DC-AC converter. And as there are obviously many electronic components working together in an EV, the motor controller monitors and measures parameters such as current, motor speed, and voltage. If errors are sensed, data related to it will be sent to external systems that alert the driver. The motor controller will then trigger a response focused on maximizing the safety of the EV and passengers inside it. For instance, if a short circuit happens within the circuitry, the motor controller steps in and stops the flow of electricity from the battery. In addition to this, the motor controller also brings down the speed at which the electric motor rotates when the battery is low on charge. This is done in an attempt to get as much juice out of the battery as possible and to maximize range. Without motor controllers, it's safe to say that EVs might just be out of control. If batteries weren't a thing, mobile phones, laptops, and electric vehicles would probably not be around. As a matter of fact, we wouldn't even be able to start conventional IC engine cars without batteries. And as technology focuses on enhancing and simplifying the way we live, batteries have become an essential part of achieving this goal. But how do batteries do this? Well, that is what this video is here to tell you. Batteries provide electrical energy through electrochemical reactions that take place within them. Here's how this happens. In every battery are two metal rods, an anode and a cathode, called electrodes. They are immersed in a chemical medium called an electrolyte that provides a conductive path for the movement of ions to and from the electrodes. When a circuit with a battery is complete, chemical reactions take place and prompt the flow of electrons through the circuit. Negatively charged electrons travel across the external circuit, and the positively charged ions move across the electrolyte. And it is this flow of charges that provides electrical energy and powers devices in its path. Before we move on, let's clear up a common confusion. While you may have heard batteries and cells being used synonymously, they are actually not the same. While a cell is a single unit of a battery pack, a group of cells connected together is what we call a battery pack. Now, coming to the two main types of cells, primary and secondary cells. Primary cells are non-rechargeable and secondary cells are rechargeable. Common examples of primary cells include dry and alkaline cells used in flashlights, remote controls, and toys. If these primary cells were used in mobile phones, we'd be replacing them each time the charge drained out. And it is to overcome this hassle that secondary cells were developed. Secondary cells are used in mobile phones, laptops, and electric vehicles. Over the course of their lifetime, rechargeable cells go through multiple charge cycles. A charge cycle is the process of completely charging and discharging rechargeable cells. Examples of secondary cells in order of their development are the lead-acid battery, nickel-cadmium battery, nickel-metal hydride battery, and the lithium-ion battery. While major manufacturers use lithium-ion batteries to power the motor due to their high energy density, the nickel-metal hydride batteries are used in hybrid EVs. To make use of the stored energy, the external circuit has to be completed. In EVs, a starter motor acts as the electrical load and is connected across the two terminals of the battery. As this completes the circuit, the battery begins to discharge. During discharge, the anode is the negatively charged electrode because it is where the electrons are generated. And since the cathode receives electrons, it is a positively charged electrode. When all the charge gets used up, the battery needs to be recharged again using an external power source, which for EVs is primarily a charging station. By recharging the battery, the chemical reactions within it get reversed and restore the electrodes back to their charged state. This is done by reversing the polarities of the two electrodes. The external power source redirects the electrons back to the anode and the positive ions to the cathode. As charging an EV battery at a charging station takes around 30 minutes or more, drivers may opt to go to a battery swapping station, where they can physically swap out their drained battery pack for a fully charged one. There are two types of battery packs used in EVs: the traction and auxiliary battery packs. The traction battery pack powers the motor that propels the EV, and the auxiliary battery pack powers various components like the headlights and infotainment systems. Although lead-acid batteries are rechargeable, their low capacity is not sufficient to power the traction battery pack. Instead, these batteries are used to power auxiliary systems in the EV. An ideal EV battery should have high power-to-rate ratio, greater capacity for longer range, and high specific energy. At the moment, the lithium-ion battery tops the list when compared to the lead-acid battery and nickel-metal hydride battery. While they all provide electrical energy to power the EV, each rechargeable battery uses its own material and medium. In fact, the same type of battery can even have different chemistries. For instance, the lithium-ion battery has 6 unique chemistries with unique properties suited for different uses. EVs commonly make use of lithium nickel manganese cobalt oxide and lithium metal phosphate batteries. Most EV battery packs have thousands of lithium-ion cells covered by a plastic casing with an insulating lid. The casing is divided into many compartments with insulating partitions in between them. Each compartment has cells connected in series or parallel. Cells in a battery are connected in series or parallel depending on the output power required. A series connection is used to improve the voltage range of batteries, and a parallel connection increases battery capacity. In some cases, a combination of series and parallel connections can improve battery efficiency. By combining many cells together, the voltage is increased to the level needed to power the EV. It takes approximately 400 to 800 volts, and sometimes even more, to power an EV. So, while a single cell may be sufficient to power your electronic devices, it is definitely not enough to power an EV. In today's day and age, lithium-ion batteries are everywhere. They dominate the electric vehicle industry with their high power density, fast charging potential, high temperature performance, and long lifespan. Being secondary batteries, lithium-ion cells can be recharged multiple times, making them ideal for use in smartphones, laptops, and EVs. But while there is just one lithium-ion cell in your electronic device, there are more than thousands of lithium-ion cells packed together in EVs to store a greater amount of energy. As EVs obviously require more power than electronic devices, the lithium-ion batteries are connected in series or parallel to increase power. But what about these batteries makes them ideal for use in EVs? Well, if we find lithium on the periodic table, it is a Group 1 element. And similar to other Group 1 elements, lithium has just one electron in its outer shell. This makes it reactive, as the electron can easily be knocked out of the atom. Combining lithium with other elements has given rise to 6 main lithium-ion battery chemistries. Each of these chemistries vary in terms of their specific energy, specific power, safety, lifespan, performance, and cost. EV manufacturers use these parameters to choose the lithium-ion chemistry that is best suited for their models. Out of all of the chemistries, there are 2 main types commonly used in the market. While some chemistries offer more range, others are safer and cheaper. To explain the chemistry behind the lithium-ion battery, we will use the construction and working principle of a lithium cobalt oxide battery. This battery has an anode made of lithium and a cathode made of cobalt in its oxide state. The lithium in the anode is held in a stable state between the layers of carbon in the form of lithium carbide. The cobalt oxide in the cathode lacks one electron and makes it unstable. When the circuit is closed, the electron from lithium in the anode is pulled towards the cobalt oxide in the cathode to make it stable. In an EV, the external circuit is completed when the starter motor is connected across the battery. When the EV turns on, electrons from the lithium atoms will continue to accumulate at the cobalt electrode. As more electrons accumulate, they begin to resist the flow of electrons from the anode. This prevents the flow of electricity. At the anode, the positively charged lithium ions get knocked out of the carbon layers and flow across the electrolyte to the cathode. And once they reach there, they join with the electrons and the charge at the cathode balances out. So when all the electrons and lithium ions have migrated, the battery gets exhausted and the cell drains out. But as the lithium-ion battery pack is rechargeable, you can charge it at the nearest charging station. By plugging the charging cable into the charging port of your EV, the external current energizes the electrons on the cobalt electrode to direct them back to the anode. And here, the lithium ions also go back through the electrolyte to get trapped in the carbon layers. This replenishes the charge at the electrodes, and the battery is ready to power your vehicle again. And now you know why lithium-ion batteries are the perfect choice for EVs. Lead-acid batteries have been around since the 19th century and are in fact the first ever rechargeable batteries known to mankind. It was only after the lead-acid battery that the nickel-metal-cadmium battery was developed. However, due to environmental concerns caused by the cadmium electrode, it was taken over by the nickel-metal hydride battery in the late 20th century. And shortly after this, the lithium-ion battery was introduced in the market. Despite the lead-acid battery no longer being used as the primary source of power in EVs due to its poor capacity and efficiency, the nickel-metal hydrides are still used in hybrid EVs like the Toyota Prius and all-electric vehicles like the Toyota RAV4 EV. They are either used on their own or in combination with lithium-ion batteries. In this video, you will learn about the construction and working of the lead-acid and nickel-metal hydride batteries. First off is the lead-acid battery, which is primarily used in IC engine cars to start the engine. Lead-acid batteries are used in situations that require intermittent supplies of electricity, and they are preferred for their inexpensive yet safe and reliable nature. Electrical energy is produced by the lead-acid battery when a chemical reaction takes place between the two electrodes. One electrode is made of pure lead, which is spongy, and the other is made of lead peroxide, which is rigid. These electrodes are dipped in a sulfuric acid solution, which acts as the electrolyte. If these two electrodes come in contact with each other, they may short-circuit the system. To prevent this, separators made of rubber, wood, or glass are placed in between the electrodes for insulation. During the discharge phase, lead peroxide acts as an anode and lead as a cathode. When the circuit is closed, the acid molecules split into positively charged hydrogen ions and negatively charged sulfate ions. The hydrogen ions, which are missing an electron, move towards the lead peroxide to gain electrons and become neutral. This electrode now becomes positively charged as it has lost electrons to the hydrogen ions. When this happens, the negatively charged sulfate ions in the electrolyte move towards the lead and transfer their electrons to the plate. As a result of these reactions, lead sulfate is formed on both the anode and cathode, leaving white deposits. So, if you pull out the electrodes and find white deposits on them, you will know that the battery was used. Now there is an imbalance of charges at the two electrodes. To neutralize the charges, the excessive negative charges on the lead plate move along the external circuit to the lead peroxide plate, thus generating electricity. Reactions that happen during the recharge phase are the exact opposite of those that happen during the discharge phase. When recharging the lead-acid battery, the connections are reversed, and this causes the hydrogen and sulfate atoms to get ionized again. They move towards the opposite electrodes, and the battery is ready to supply electricity. Lead-acid batteries are classified as either flooded or sealed batteries. Flooded lead-acid batteries are widely used in the automotive industry today. They are called flooded batteries because the acidic electrolyte solution is free to flow around the battery casing. Oxygen and hydrogen gases produced during the discharge phase are released via openings in the casing. Since there's a chance that the acid can leak from these openings, they have to be positioned strategically. Moreover, water can evaporate from the electrolyte solution due to the heat generated from the chemical reactions. This is why distilled water needs to be refilled in the battery at regular intervals. Sealed lead-acid batteries, on the other hand, have a completely enclosed casing. The electrolyte is in a gel state rather than a liquid state to prevent leakages. The oxygen and hydrogen gases produced combine to form water. This water is used to keep the gel from drying up. However, a cleverly designed vent is installed for the excess hydrogen to be released. If this hydrogen gets trapped within the housing, it may ignite due to high temperatures. And for this very reason, it is called a valve-regulated lead-acid battery, or VRLA. Lead-acid batteries lose out to lithium-ion batteries because of their poor performance in cold temperatures, low energy density, lifespan, and range. It is these very limitations that put the nickel metal hydride battery in the lead in the automobile industry. Nickel metal hydrides have a cylindrical casing with a metal hydride anode on one side, a nickel cathode on the other side, and a potassium hydroxide electrolyte. When the anode and cathode are dipped in the electrolyte solution, electrons are lost and gained at the respective electrodes via the external circuit. During the recharge phase, the reactions are reversed, and the charges get restored when the ions recombine to form the metal hydride and nickel. But why do some car manufacturers still opt for the nickel metal hydride battery when the lithium-ion battery is around? Well, when compared to the lithium-ion battery, the nickel metal hydride battery can actually withstand extreme ranges of weather conditions, making it all the more resilient. So there you have it, the basics of the lead-acid and nickel metal hydride batteries. While they may be considered archaic battery technologies, they are still around and serving their purpose in the EV industry. With the single-speed transmission system, electric vehicles can go from 0 to 100 kilometers per hour in just a matter of seconds. EVs have a transmission system just like other vehicles that uses power to turn the drive wheels. But unlike IC engine cars that have a multiple-speed transmission system, EVs have a single-speed transmission system that gives maximum torque right from the start. This makes it high revving, giving it up to 20,000 RPM. While EVs are powerful from the get-go, IC engine cars require frequent gear shifting to convert narrow ranges of usable torque and power to much higher ranges needed on the road. In fact, this transmission system only gets the IC engine car up to around 7,000 RPM and has a complex and heavy gearbox that brings high maintenance costs to users. The multiple gears in IC engine vehicles work on the concept of specific ratios. But this is not the case in the single-speed transmission system in EVs, which has a single fixed reduction gear. This basically means that the motor runs at speeds higher than that of the wheels. Let's take a look at how the single-speed transmission system works from the time you press the accelerator pedal. When you press down on the pedal, a corresponding amount of current is sent to the motor controller. The motor controller feeds this current to the electric motor that draws power from the battery to rotate. As the shaft of the electric motor is connected to the drive gear in the gear system, it rotates along with the electric motor. When the drive gear rotates, it also rotates the driven gear. The drive gear in the gear system is connected to the differential that drives both wheels and lets them rotate at different speeds when needed. For instance, when turning a corner, the wheel on the outside has to rotate faster than the other. EVs can move forward or backwards with just the press of a button. This is because the electric motor can rotate both clockwise and anti-clockwise depending on the direction of current. In order to reverse the direction of current, the driver just has to press the reverse button. When the direction of current gets reversed, the polarity of the electromagnet in the motor also changes. This makes the motor rotate in the opposite direction, which in turn reverses the direction that the car travels. When it comes to EVs, there are 4 different drive wheel systems used. In front-wheel drive, the electric motor is at the front of the vehicle, and in rear-wheel drive, the electric motor is located at the rear end of the vehicle. EVs also come in 4-wheel drive and all-wheel drive systems. Both systems require the placement of an electric motor at the front and back axles of the vehicle. Although they may seem similar, they differ in the way they power the wheels. All-wheel drives power the front and rear wheels simultaneously. The main difference between all-wheel and 4-wheel drive system is that the latter can choose to send power to either the rear or front wheels. It can also decide whether it sends power to all 4 wheels. This allows the driver to choose which wheels the power is sent to with just a switch or lever. As the single-speed transmission system has a single fixed reduction gear, it is relatively simple and user-friendly. The inner mechanical workings and movement of the parts in the gearbox often wear out and may break down. All of this is avoided in the single-speed transmission system as construction is simpler and ultimately cuts down the overall maintenance costs. So, with electric vehicles, you can say goodbye to the Prindle system and shift gears to single speed. Batteries, motors, and converters are all things we hear about when it comes to the electric vehicle. But it is the chassis of the electric vehicle that actually brings these parts to life. While the chassis supports the load of structures, passengers, and systems in all vehicles, the role of the EV chassis goes a step further. This is because all the components are built in and integrated into the chassis, making it a self-contained platform. If you've ever seen what the chassis looks like, it's pretty much similar to a skateboard, with a platform and wheels on 4 corners. And this is why the chassis used in electric vehicles is called a skateboard chassis. This platform offers a base structure for the motor, batteries, wiring, and other electrical components to be mounted on. For instance, models of Tesla, as well as the Mahindra E2O, are designed with a skateboard chassis to efficiently accommodate the power components. In fact, the skateboard chassis is a universal chassis configuration adopted by EV manufacturers that lets them build their own variation with the base design. The chassis can be scaled to fit different sizes and be fitted with a range of vehicle bodies. This saves the time manufacturers spend developing a chassis for each model from square one. There are, however, a few vehicles like the Tata Nexon that do not use the skateboard chassis because they swap out the conventional IC engine with EV components instead. This does not change the mechanical structure or chassis of the EV. But by using a skateboard chassis, space efficiency can be improved because having the components mounted on the platform minimizes the amount of space they take up. This offers more room for passenger space in the vehicle. While the battery pack is equally distributed along the chassis of the vehicle, the electric motor is placed at either or both ends of the vehicle depending on the drive configuration. This distribution of the EV battery pack along the platform of the chassis lowers the vehicle's center of gravity, improves handling, and provides more stability during collisions. Placing the battery pack at either front or rear ends of the vehicle will increase the load in one specific location of the chassis and shift the center of gravity towards that location. Among other factors, the shift in center of gravity is one that can cause understeering or oversteering. If the center of gravity is closer to the front end of the vehicle, it is prone to understeering. And if the center of gravity is closer to the rear end of the vehicle, it is prone to oversteering. Having the battery pack at either end of the vehicle puts it at risk of direct impact during a collision and poses a safety hazard for the passengers. Although the EV battery pack contributes to the majority of the vehicle's weight, the platform of the skateboard chassis provides much scope for reducing weight to improve fuel efficiency and handling. When designing the chassis and selecting the material to use, the primary focus is on supporting the load of the vehicle and passengers within it. Both advanced high-strength steels and aluminum find themselves competing to be used as materials for EV chassis in the automotive industry. Even though steel is preferred for its strength, crashworthiness, performance, durability, and low cost, it does happen to be relatively heavier than aluminum. As aluminum weighs relatively less, it is a preferred choice for use in EV chassis. But when the steel industry developed high-strength steels with strengths up to 2,000 megapascals, it took the lead in recent EV models such as the Tesla Model 3. As research into optimizing designs for skateboard chassis continues, it will definitely pave the way forward for the future of electric vehicle design. Electric vehicles are a combination of electronic and electrical components working together. They have a constant flow of electrical energy and information through the many wires that connect these components. You just don't see all the wires because they are bound together by a wiring harness that is a collection of wires, their terminals, and connectors held together by a durable and insulating material. The wiring harness is designed in such a way that multiple wires are organized into several bunches that follow specific routes along the body of the vehicle. Not only does this simplify handling, but it also reduces the chance of short circuits in the system. It also optimizes the way space is used in the electric vehicle and protects the wires from external damage. EVs have wires that run on for miles on end, and having them loosely lying around the vehicle would prove to be an inconvenience. But it isn't as simple as just taking the wires and putting them together. Before a wiring harness is developed, it is vital to model and simulate the positioning of components and the route of wires. It has to be designed in a way that efficiently uses the space in the EV while making sure that all necessary components are connected. Behind the design of a wiring harness are four main steps. These include selecting the components and their placement, the wiring diagram, selecting the right harness, and electrical routing. Before the path of wires can be designed, the components along its way needs to be selected. These include high-voltage components like the battery pack, motor, and inverter, as well as low-voltage components like lights, fuses, relays, tubes, and sensors. Next comes the placement of these vehicles in a circuit to develop a wiring diagram. The components are laid out and connected together. After the components and wires are positioned appropriately, the wiring harness is designed. Specific design requirements are taken because the harness passes through parts of the vehicle that are exposed to heat and moisture. The 3D design of the wiring harness gets converted to a 2D diagram through a process called flattening. Flattening provides accurate measurements and manufacturing specifications that can be used by manufacturers. And last is electrical routing, where the course of the wiring harness through the EV is visualized. The flattened diagram tells us the path the wires run through the vehicle and the length of the harness needed. This is called routing and makes sure that all components are connected without interfering with each other. It also assembles the path in which electricity will flow through the components to minimize complexity caused by the wiring harness running through the vehicle. The design of a wiring harness takes the difference between high and low voltage systems into account. High-voltage wiring harnesses are used for DC voltages beyond 250 to 750 volts, and low-voltage wiring harnesses are used for DC voltages less than 250 volts. A high-voltage wiring harness connects components that work on high voltages, like the battery, motor, and inverter of an electric vehicle together, as they are a part of the high-voltage system. The battery and inverter are connected together by an underfloor wiring harness which is longer in length than the power cable connecting the battery and motor together. In order to prevent interference caused by electromagnetic noise, both harnesses require shielding, as the underfloor harness has protectors to shield wires from external damage. Each component is connected by 2 wiring harnesses to split the load. In the electric vehicle, the wiring harness begins at the charging port where you plug it into the charger. It then goes on to the onboard charger that converts AC to DC. And from here, the wiring harness goes to the rapid splitter. The rapid splitter plugs into the battery pack and is also the point where the connection splits into 2 routes. While one route goes to the motor supply, the other goes to the high-power distribution module. As the motor is responsible for acceleration and deceleration, the motor supply route is connected to the transmission. The high-power distribution module is connected to the air compressor, battery heater unit, DC-DC converter, and the positive temperature coefficient cabin heater. While the high-voltage system connects these components, a cell or module from the high-voltage battery pack powers the components of the low-voltage system. The DC to DC converter brings down the high voltage from the battery pack to a lower voltage level that can be supplied to the auxiliary electronic systems. This converter connects to a 12-volt lead-acid battery. The total load is shared between the lead-acid battery and the DC to DC converter. From here, electrical energy flows to each individual component of the low-voltage system, such as the headlights, taillights, and wipers. A primary difference in the wiring harness of EVs and IC engines is that the EV has a high-voltage system with many wires. Each vehicle model has its own wiring harness configuration. Since the wiring harness system is made by hand, it comes at a high cost. They also prevent safety hazards caused by exposed wires and disorganized circuits. So, having an organized wiring harness keeps the electrical energy flowing through the system in a safe and efficient manner. If the temperature of the human body increases or decreases beyond the ideal range, it might lead to unpleasant effects that affect your overall health and performance. For example, if you're running at temperature, you may experience sweating, headaches, weakness, and shivering that hamper body functions. And the same goes for when you're cold, but instead of sweating, the body shivers in an attempt to increase temperature back up to the normal range. Unwanted effects of temperature fluctuations are not limited to just the functions of the human body. The performance of an electric vehicle is also put to test when the temperature of the battery pack, electric motor, and motor controller go beyond their normal operating range. Similar to the way the human body monitors and manages temperature, EVs are equipped with a thermal management system, or TMS, that is designed to monitor and control the temperature of the battery, motor, and motor controller. When electricity flows through batteries during charge and discharge, it generates heat because of electrical losses. If this heat is not managed and eliminated appropriately, it may limit the performance of the EV or pose a safety hazard to passengers inside it. And just like how our bodies need an ideal temperature range to feel and function well, batteries also have a range at which they demonstrate optimal performance. In fact, if their temperature goes above or beyond this range, it may lead to cell degradation. The battery pack may also be prone to thermal runaway, where the amount of heat developed inside the battery crosses the amount of heat released to the surroundings. Over time, this heat accumulation can damage the battery. When the temperature of the battery is managed, the overall health of the battery can be preserved. This in turn helps the EV achieve maximum range and performance. While thermal management is essential for the battery pack, the TMS also ensures that the temperature of the electric motor and motor controller are maintained within the optimal range. If the temperature of these parts rise, they are prone to catching on fire, which stops the working of the system. And if the motor in an electric vehicle stops working, the EV ceases to move. In order to prevent issues in the electric vehicle because of overheating, the TMS cools the parts using one of three methods: liquid coolants, air cooling, or cooling fins. Here's a quick look at each one. Circulating a liquid glycol coolant through the internal circuitry is the most dominant method of cooling used in EVs. Many car manufacturers like Tesla, BMW, Chevrolet, Audi, and Jaguar employ this method. The entire cooling loop is connected in series. It starts off cooling the battery pack, moves on to the motor, and then the electronic systems. When going through the battery pack, glycol from the reservoir passes through the tube surrounding each of the cells. The tube snakes between the cells to maximize the amount of contact between them. As it moves along the cells, it absorbs the heat generated by them and dissipates it to the air through the radiator. For cooling the motor and motor controller, a coolant-to-oil heat exchanger passes oil through the grooves in the stator of the motor. This system also absorbs the heat and releases it via a radiator into the air. Coolants like glycol are used for their low freezing points, high thermal conductivity, and high heat capacity. Used to a lesser extent is the air cooling method, which involves circulating air over the top of the parts. It will absorb the heat, move it away from them, and into the air. However, this is not a preferred method as air has poor heat conductivity. Cooling fins are also used to cool the system as they increase the surface area needed for heat transfer to take place. When the heat gets transferred to the cooling fins from the battery pack through conduction, it is transferred to the air via convection. But as they add more weight to the EV, it's not a preferred method of cooling. But thermal management in an EV goes beyond just cooling the battery pack, as it also involves heating the battery pack in low temperature conditions. This is because battery capacity is greatly reduced under low temperature effects. And now you know that temperature control is just as important in electric vehicles as it is to the human body. We've all heard this at one point or another. Energy can neither be created nor destroyed, but it can be transformed from one form to another. And it is this very law that the regenerative braking system in electric vehicles exploits. When the brake is pressed, the regenerative braking system converts kinetic energy, generated by the movement of the car, into electrical energy that can be stored in the battery. Let's break it down for you. It takes a certain amount of kinetic energy to get the car going when you press the accelerator pedal. But when you press the brakes, this energy has to go somewhere, so it can't be lost. It can only be transformed into another form. In the average vehicle without regenerative braking, pressing the brakes converts the kinetic energy into heat energy. And as heat cannot be put to good use in these vehicles, the energy eventually gets wasted. But in EVs, this energy is used to recharge the batteries. Releasing the accelerator pedal decelerates the electric car, and when the car decelerates, the motor also slows down until it stops. Since the drive wheel is attached to the motor, it continues to be in motion before gradually coming to a stop. At this stage, the motor acts like a generator, during which it takes the kinetic energy of the wheels and converts it into electrical energy that can charge the battery. As the vehicle decelerates, a back electromotive force, or back EMF, develops. The electricity that comes from this is what gets stored as electrical energy in the battery. So in EVs, the electric motor happens to be an energy recovery device that acts as a generator when braking. The regenerative braking system can be used in battery EVs as well as hybrid and plug-in hybrid EVs. In all vehicles, the amount of energy returned to the battery during regenerative braking depends on how the driver operates the vehicle. More energy is reaped when drivers gradually decelerate the vehicle, as it gives the EV time to capture and transform the kinetic energy. Drivers who abruptly hit the brakes find regenerative braking to be less efficient and not enough time is given for the system to convert energy. Regenerative braking is also more effective when drivers are on the roads that require them to press the brakes more often. This is because it gives the electric motor more opportunities to capture and transform energy. Now that we have covered how regenerative braking works, here's a look at its pros and cons. By being able to top up energy when on the go, the regenerative braking system saves energy and maximizes driving range by extending battery life. The amount of energy the regenerative braking system can capture depends on factors like braking force, braking power, charge left in the battery, and how the EV is being driven. But generally, anywhere between 16 to 70% of the kinetic energy can be captured and stored as electrical energy. Another limitation is that not enough kinetic energy is generated at lower speeds for the regenerative braking system to capture and convert into electrical energy. At higher speeds, the system may not always bring the EV to an immediate halt, which in certain cases may jeopardize safety of passengers in the EV. In some cases, drivers used to the conventional braking system have expressed discomfort in the pedal of vehicles with regenerative braking systems. Until they get accustomed to it, they may not be comfortable working the brakes. Nonetheless, the regenerative braking system is breaking the norms of how we brake. From analog watches to smartwatches, and IC engine cars to electric vehicles, advancements in technology are endless. Technology has found its way into almost all aspects of modern life, making it just that much faster and smoother. In the automobile industry, technology is changing the way we accelerate, brake, and steer cars. The conventional drive-by-cable system using mechanical linkages and hydraulic pressure to manage the functions of a car is now being replaced with the drive-by-wire system that operates a car with just electronics. In place of the mechanical connections found in drive-by-cable systems, the drive-by-wire system brings in an electronic unit to manage acceleration, braking, and steering. And as their name suggests, acceleration is handled by the accelerate-by-wire system, braking by the brake-by-wire system, and you guessed it, steering by the steer-by-wire system. Petrol engines were first to be equipped with drive-by-wire technology, replacing the traditional drive-by-cable system. In a drive-by-cable system, the accelerator pedal is connected to a cable, and the other end of the cable is attached to a valve that opens or closes to draw fuel in. Depending on how much you push the accelerator pedal, the corresponding amount of fuel is taken in and ignition is initiated. Upon release of the accelerator, a spring mechanism shuts the valve. But since this involves more mechanical movement, it takes relatively more time for the valve to respond to user input. The same job, when performed by drive-by-wire systems, uses sensors and actuators. While sensors provide inputs, actuators provide outputs. So when you push the pedal, a sensor beneath the accelerator gets activated and signals how much the valve should open. At the end of this setup is an actuator that activates the mechanical system. This makes the input and output process mechanical, with an electronic system in between. While many cars still use the drive-by-cable system, the accelerate-by-wire system is extensively used in electric vehicles these days. In EVs, pressing the pedal activates the sensor, which then sends a corresponding voltage to the motor control unit, or MCU. Voltage sent to the MCU increases as you press harder on the pedal. Since the extent to which the pedal is pressed is proportional to the electricity supplied to the motor, there is greater harmony between the accelerator and the torque produced. When we hit the brakes in the drive-by-cable system, pressure gets magnified by a hydraulic brake booster, which then sends it to the brake calipers. The brake-by-wire system removes the direct connection between master cylinder and brake pedal. In vehicles with electro-hydraulic brake-by-wire systems, the hydraulic calipers are activated through sensors, based on how much the brake is pushed. The MCU decides how much braking force is needed at each wheel. This then triggers the hydraulic calipers accordingly. Electromechanical brake systems further remove connection between driver and brakes, as they do not have a hydraulic component. They solely rely on sensors to determine how much braking force is needed. In place of the force being transmitted by hydraulics, the actuators trigger the brakes in each wheel. In brake-by-wire, electrical systems are coupled with hydraulic and mechanical systems because regulatory constraints do not allow the production of fully drive-by-wire systems, as other linkages must be present to take over in the case that electric systems fail. So far, we've covered how the drive-by-wire system accelerates and brakes a car. Now let's go over how it steers a car. In traditional drive-by-cable designs, a rack and pinion steering gear system is used. So when the driver turns the wheel, a proportional turn reflects in the steering wheels. Vehicles with the steer-by-wire system have no connection between tires and the steering wheel. Instead, when the driver turns the steering wheel, a corresponding signal is sent to the MCU that then conveys the message to the electric motors. Now, you may wonder why we need an alternative to the traditional drive-by-cable system. Well, the drive-by-cable system, with many mechanical linkages, starts to wear off over time and becomes less responsive. It requires more maintenance and makes the car heavy. By activating mechanical parts of a car with the drive-by-wire system, we can reduce the number of moving parts in the vehicle, making it easier to maintain. Even more so, drive-by-wire facilitates uniformity between driver input and vehicle output, providing us with a smooth user experience. Now, the cool thing here is that depending on how hard you press down on the pedal, the amount of current sent to the motor controller varies. So if you put the pedal to the metal, more current is sent to the motor controller and the faster you go. As the drive-by-wire system is simple to use, it is considered a reliable system when compared to drive-by-cable. It is these very advantages that drove automotive companies like Tesla, Fiat, Volkswagen, and BMW to implement parts of the drive-by-wire technology for their vehicles. Imagine charging your electric vehicle beyond its limit and later finding out that the battery pack has been damaged. And if the battery pack gets damaged, it poses a safety threat to all those in and around the vehicle. It is to prevent hazards like this that electric vehicles have a battery management system, or BMS, to keep them in check. The BMS oversees the workings and performance of the rechargeable lithium-ion battery pack in EVs to make sure they function efficiently within safety limits. The BMS does this by monitoring the temperature and environment of the battery, flow of coolant through the circuitry, and estimating and managing state of charge and state of health. By doing this, battery performance and life can be maximized through cell balancing. An EV battery pack is made up of many lithium-ion cells connected together in a series, or parallel. Each cell has its own state of charge and capacities because no two cells are like each other. Even if one of the cells in the battery pack drains out, the entire pack stops working. Cells that drain out first curb the energy potential of the entire battery pack, and this is why the energy has to be equally distributed or balanced among the cells. Cell balancing redistributes the energy available in a battery pack consisting of many cells in a circuit. By doing so, the energy and lifespan of the cells is improved. Cell balancing is also required to prevent issues that may arise within the battery system, like thermal runaway, cell degradation, or incomplete cell pack charging. Since lithium-ion batteries are sensitive to overcharging and discharging, they are prone to thermal runaway, where the amount of heat generated within the battery crosses the amount of heat that can be released. As time goes on, lithium-ion batteries also undergo cell degradation that is marked by a reduction in their lifespan, efficiency, and capacity. By balancing the charges of cells within the battery, their condition can be preserved to delay the effects of cell degradation. Similar to how some cells drain out before others, some also reach their full capacity faster. Because of this, cells that are not fully charged may be mistaken as fully charged. This results in incomplete cell pack charging. But how does cell balancing actually work? There are two methods: active and passive balancing. Imagine you have a barbell with 16 kilograms of weight on one side and 20 kilograms of weight on the other side. If we apply the concept of active balancing, 2 kilograms from the side with 20 kilograms would be taken and added to the side with 16 kilograms. This would equally distribute the weight across the barbell, giving us 18 kilograms on both sides. Now, if we apply the concept of passive balancing, 4 kilograms would be removed from the side with 20 kilograms, giving us 16 kilograms on both sides. In both active and passive balancing, we have equally distributed the weights. So in terms of cells, active balancing transfers energy from a cell with more charge to a cell with less charge in order to equalize the charge within the battery pack. This can be achieved through charge shuttling, which involves transporting energy from one cell to another, or by energy converters, which use capacitors, transformers, or inductors to facilitate the movement of energy across cells. On the other hand, passive balancing is when charge is drained from the cell with more charge and dissipated in the form of heat. This is done by adding a resistor to the circuit. Active and passive cell balancing have their own set of pros and cons. Active balancing does enhance the performance of the cell. Passive cell balancing is cheaper than active cell balancing, but this method has poor efficiency in transferring energy. Since cell balancing equally distributes the state of charge across cells, here is a quick overview of what it is. On every mobile phone is a battery symbol with a percentage next to it. And this percentage actually represents your phone's state of charge, which is nothing but the amount of energy left in your phone's battery. EVs also have a battery gauge which indicates how much charge is left in it. Parallel to the battery gauge, in an IC engine car is the fuel gauge that indicates how much fuel is left in the tank. It is important to note that the maximum your battery can be charged is always less than its full capacity. Cells are configured this way to improve the lifetime and performance of the battery. Batteries, just like humans, age and deteriorate over time. And just like we monitor our health, it is important to monitor a battery's state of health. However, through repeated cycles of charge and discharge, their condition declines over time. The state of health of a battery is determined through comparing its current condition with its optimal performance. Lithium-ion batteries used in EVs are no exception to the effects of degradation. Ergo, the BMS evaluates the state of health of the battery pack and reports on its status to prevent pitfalls in EV performance. As lithium-ion batteries generate a lot of heat, the BMS monitors temperature fluctuations to ensure they stay within the optimal range. If the temperature goes below or above this range, EV performance is likely to be affected. During intervals of high temperature, the BMS activates the cooling system. Monitoring the temperature of an EV battery pack is also essential for the safety and comfort of passengers within the vehicle. So in a nutshell, we can't have a battery pack without a BMS. Just like the battery symbol and percentage on your mobile phone is one on your electric vehicle's display. This lets you know how much charge is left in your EV's battery pack, which in other words is the state of charge. As batteries go through multiple charge cycles over the course of their lifetime, their condition declines because of the constant flow of current through them. The more current flowing through them, the more heat generation and a faster reduction in battery capacity. This is why the battery on your mobile phone can't store charge for long durations as it ages, because of which you end up charging it more often. The same goes for the battery in electric vehicles as well. This makes it vital to monitor the battery's state of health, which is its condition at a given time compared to its performance under ideal conditions. Evaluating and reporting on the state of charge and health of an electric vehicle's battery is taken care of by the battery management system. But how do we measure the state of charge and health of a battery pack? Well, since there are no direct methods of determining the SOC and SOH of a battery, we use methods of estimation instead. For this, factors that can be measured such as the current, voltage, temperature, and model of the battery are taken into consideration in order to arrive at an SOC and SOH estimation. Estimating the SOC of an EV battery pack lets the driver know how long the battery can run for before they need to change it again. It also protects the battery from overheating due to overcharge or discharge, which if not controlled can affect battery health. While there are a series of methods used to estimate the SOC of a battery pack, there are three main methods used when it comes to EVs. These include the Coulomb counting method, open circuit voltage method, and the Kalman filter algorithm. Here's a look at how they work. The Coulomb counting method, or the current integration method, determines the SOC of a battery pack by integrating the amount of current entering and exiting the pack with time. This is done with a column counter that is connected across the battery. The results then get displayed as the SOC. Next is the open voltage method, which is a direct measurement of battery SOC. Open circuit voltage is the difference in potential between the two terminals of a battery when no load is connected across. The SOC of a battery is related to its open circuit voltage. For instance, in a lead-acid battery, the relationship between the SOC and open circuit voltage is almost linear. But the only drawback of this method is that this relationship is not linear for all battery types, and this mainly holds true for lithium-ion batteries. New adaptive systems have been developed with advancements in artificial intelligence. One commonly used adaptive system is the Kalman filter. This is an estimation algorithm using real-time data on terminal voltage, which is the difference in potential between the two terminals of the load when the circuit is on. The Kalman filter algorithm is used because it limits noise interference from sensors and provides more accurate readings. Once the sensors measure electric charge and voltage, they display it for the driver to see as the battery and percentage icon on the display panel. When aware of the battery's state of charge, they can monitor its performance and optimize it for use on the road. The usable capacity of a battery is influenced by factors such as the age of the battery, its internal and external temperature, and charge and discharge rates. Their effects are not limited to just SOC, but also extend into the battery's SOH because over time, they affect parameters such as internal resistance, capacity, and battery voltage. The relationship between state of charge and state of health is defined by the equation where the rate of change in state of charge is the difference between the rate at which state of health and depth of discharge change. Here, depth of discharge is just how much charge has left the battery. This is the inverse of the SOC. So, if your electric vehicle has 60% charge left, 60% corresponds to the SOC, and the 40% that left the battery corresponds to the depth of discharge. Unlike SOC, which has methods of estimation, the SOH of a battery does not. Instead, the battery management system in EVs makes use of a series of physical parameters such as internal resistance, voltage, and capacity to determine the health of the battery pack. In a brand new EV, the state of health should ideally be 100%, but with usage over time, this percentage is inclined to decrease. The battery of an average electric vehicle offers 300 kilometers of range on one charge, and is expected to last a good 10 to 20 years before needing replacement. So, getting the most out of your battery is about more than just charging it. Electric vehicles are electrifying the automobile industry as we speak. By minimizing the use of fossil fuels in the industry, the EV is on the road to reducing pollution and saving the world. Like all things electric, EVs get their energy from an external power source that provides the electrical energy needed to charge their batteries. And as fuel stations are to IC engine cars, EVs are to charging stations. So if you want to charge your EV, you pull up to a charging station and not a fuel station. But it isn't as simple as it sounds. Filling up an IC engine car is a routine and quick process. You go to the fuel station, they fill up your tank, and you're ready to go in just a matter of minutes. But the same does not apply for EVs. Not only do they take more time to charge, but different EV models also vary in the amount of power they can receive. And this is why EV charging comes in 3 levels: Level 1, 2, and 3. Level 1 charging makes use of the average outlet available at home. So this means that using this level of charging gives you the flexibility to charge your EV in the comfort of your own home. But they take hours to fully charge the vehicle and only give up to 5 miles of range per hour of charge. Level 2 charging takes it up a notch and uses outlets of greater voltage. These are commonly found in commercial locations but can also be installed at home. They offer faster charging than Level 1 charging and provide up to 20 miles of range per hour of charge. Both Level 1 and Level 2 charging options feed electrical energy in the form of alternating current to EVs. An onboard charger is a system onboard the vehicle that performs the AC to DC conversion. And if there is an onboard charger, it's only right that there's an off-board charger. Off-board chargers are used in the case of Level 3 charging, also known as DC fast charging. Instead of the AC to DC conversion taking place within the EV, it takes place outside, and that's why they're called off-board chargers. DC fast charging saves on the time that Level 1 and 2 take to convert alternating current to direct current. Since it directly feeds DC into the EV, it can provide up to 80 miles of range per hour of charge. But as specialized installations are needed for fast charging, it is only compatible with a few EVs. DC fast charging is further divided into 3 charging systems. These include Charge to Move, the combined charging system, and Tesla supercharging. Each of these methods have different types of connectors that plug into the socket of EVs. Here's a quick overview of each one. Charge to Move, or CHAdeMO, which literally means move using charge, is the first ever fast charging method started by Japanese car manufacturers. It can provide 6 to 150 kilowatts of power. The combined charging system is a universal standard of charging that combines AC and high-speed DC to charge an EV, and offers 80 to 150 kilowatts of power. All EV charging stations are equipped with Charge to Move and combined charging system connections. Tesla EVs, on the other hand, have their very own fast charging system called Tesla Supercharging that gets the job done quick and easy for Tesla users. But as not everyone has access or the installations needed for DC fast charging, a quicker alternative may be stopping at a battery swapping station. They're pretty much what the name suggests: a station to swap out your drained batteries for a fully juiced one. While there are external ways of charging your EV, it actually has its own way of harvesting energy inside it through the regenerative braking system. This is a form of energy harvesting because kinetic energy from the movement of the wheels is converted into electrical energy that charges the battery. At the core of this mechanism is the electric motor. When you're on the go, the motor focuses on propulsion, and when you hit the brakes, the motor focuses on recharging the battery. So the moment you hit the brakes and let go of the accelerator, the motor starts to recharge the battery. Talk about self-sufficiency. As good as this sounds, it only works when the battery has room to allow more charge in. If the battery is at maximum capacity, it will not accept any more charge. Now imagine a world where you could charge your EV by just driving on a road or when parked at a parking lot. This is actually just wireless charging that you've probably come across before. If not for an EV, wireless charging is common for mobile phones. All you do is place your mobile phone on a charging pad that uses electromagnetic induction to charge the device. This same principle works for EVs too. Although not quite as common yet, EVs can also be wirelessly charged. All you have to do is park your EV on top of a coil system that is built into a space like a garage, parking lot, or even the road. And while this may sound like a futuristic concept, it might just become reality and switch up the EV charging game. Just like AC and DC motors are used to drive the electric vehicle forward, There's another set of motors called reluctance motors. Even though all these motors have the same function, their working principles are anything but the same. While AC and DC motors work on the interaction between magnetic and electric fields, reluctance motors work on the principle of reluctance and come in two main types: the switched reluctance motor and the synchronous reluctance motor. The reluctance of a material refers to its ability to resist the flow of magnetic flux. If you look at the magnetic flux of a permanent magnet, the magnetic lines pass through air and move from the North Pole to the South Pole. These magnetic lines always follow the path with least resistance. Although it might be hard to imagine, air does resist the passing of electrical and magnetic energy through it. But if you place an iron nail in the magnetic field, the magnetic flux tends to pass through the nail. This is because iron's resistance towards letting magnetic flux flow through it is far less when compared to the resistance offered by the air. Every material, for instance the iron nail, has magnetic domains, which are areas in it that are magnetized in the same direction. Different areas of the iron nail will have varying magnetic domains. When a magnetic flux passes through it, the alignment of the domains change to be in one uniform direction. This gives the nail a temporary north and south pole, and is what attracts the nail to the opposite pole of the permanent magnet. Now that we know the basics of reluctance, here's a look at how it relates to a simple reluctance motor setup. If we replace the iron nail with an iron bar that acts as the rotor, and put it in the middle of two electromagnets that act as the stator, one positive above and another below it, the iron bar would behave the same as it would with a permanent magnet. This means that it will get attracted to the opposite poles of the electromagnet because the magnetic flux of the electromagnet chooses the path with least resistance, which happens to be through the iron bar. The rotor, trying to align with the stator, is what causes the rotational movement that produces torque and power. However, when the opposite poles of the rotor and stator actually align with each other, they stop rotating and generate zero torque. It is to overcome this break in rotation that synchronous reluctance motors have three-phase windings carrying a three-phase AC around their stator. To understand this better, let's look at the working of a synchronous reluctance motor. A synchronous reluctance motor has a stator with three-phase coil windings, a rotor, and a shaft. When the coil windings are excited, a rotating magnetic field is generated by the stator. The magnetic flux then seeks to move through the path of least resistance. So, ideally, the rotor will move towards the opposite ends of the stator in order to align with the magnetic field. But due to a delay in the domains of the rotor aligning, the rotor rotates with low inertia. So instead of continuing to rotate when the opposite pole approaches, it causes a repulsive force. In order to overcome this delay, the speed of the RMF can initially be reduced to give the rotor time to catch up. A controller device can detect the position of the rotor and vary the RMF speed as needed to ensure that the attractive force is always present between the rotor and RMF. This magnetically locks the rotor with the stator's magnetic field and generates a continuous torque. It is this continuous torque that is sought after by car manufacturers in the EV industry. Switched reluctance motors also function on the principle of trying to find the path of least reluctance. They are popular for not having a permanent magnet material. However, when looking at it from a power converter point of view, they have complex driving requirements. These motors have different configurations that vary the stator to rotor pole ratios. In this video, we will be using a motor with a 6:4 stator to rotor pole ratio. When the stator is energized, it develops a magnetic field that reduces reluctance by minimizing the air gap. When opposite stator poles are energized, the rotor aligns with them. So by energizing successive stator poles, the rotor will keep aligning. This is what generates the rotation. When the rotor is aligned with the stator, it has minimal reluctance. And when it is unaligned with the stator, it has maximal reluctance. When two rotor poles align with opposite stator poles, there is another set of rotor poles that get unaligned to a different set of opposite stator poles. The unaligned set of stator and rotor get excited to align again. So in this case, the current would be switched to this set of windings to generate a movement. This movement is what provides power and torque for the electric vehicle. It is called a switched reluctance motor because current is switched on and off for successive stator windings. Since this motor has no permanent magnet, it can tolerate greater forces from magnetic fields than current-carrying conductors. They can be used in combination with driving equipment without needing gearboxes or power transmission equipment. This saves costs and gives high power and torque density, efficiency, and a robust structure. As the electric vehicle industry is all about finding simple and efficient motors, the reluctance motor might just be the answer. As more drivers switch to electric vehicles, there's an exponentially increasing demand for the electrical energy that powers them. This is pretty much similar to the constant demand placed on fuel by IC engine cars. But there's a difference. Electric vehicles need to stay plugged into the charging station to charge their battery pack. Now, what would happen if most electric vehicle drivers chose to charge their vehicles at the same time? For instance, it is convenient for drivers to plug in their electric vehicle at night so that it is ready to go in the morning. While this may be convenient for the driver, it places a heavy demand for electrical energy on the power grid, because of which it experiences a peak load. It is to manage and control situations just like this that smart charging systems have been developed. Smart charging is a charging system that allows charging operators, charging stations, and electric vehicles to share data regarding their state of charge and the demand at the power grid. It also oversees and controls the use of charging devices and the flow of electrical energy to maximize the efficiency of charging and energy consumption. It decides how much electrical energy to give the electric vehicle when plugged in by studying the number of people charging their EVs at that time, as well as the overall demand for electrical energy in that area. When more EVs are plugged in, there is a high demand in energy during which the charging system may opt to reduce the amount of power given to the vehicle. In some cases, the smart charging system may hold off on charging the electric vehicle until a later time when the demand is less. By doing this, the burden on power grids is reduced and ensures that charging stations are not maxed out of the amount of electrical energy they have. This is known as peak shaving and is when peak energy demands are spread out over a longer duration. Now that we have gone over what a smart charging system is, here's a look at how it works. This charging system is similar to a cloud network where information can be shared. When you plug in an electric vehicle at the charging station, it sends this information to the cloud platform through Wi-Fi or Bluetooth. This information then gets studied, interpreted, and visualized to determine when and how to charge the EV. Through this process, there is efficient control over the flow of electrical energy. EV drivers can even pay and keep track of their charging sessions through their mobile applications on their phones. These apps also let them track the charge of their electric vehicle and the electrical energy in charging stations in and around them. Users can even specify how much their electric vehicle is to be charged before a specific time. Smart charging systems can be implemented in 3 different ways: V1G, V2G, and V2H to B. V1G is a unidirectional relay of electrical energy from the power grid to the vehicle. This is when charging stations adjust their rate of charging according to the demands on the power grid. V2G, or vehicle-to-grid charging, is bidirectional, as electric vehicles can either be charged or discharged. When there is a high demand for electrical energy at the power grid, electric vehicles can give back energy to the grid. When the peak demand on the power grid reduces, the electric vehicle will then be charged back up again. V2H to B, or vehicle to home or building, is when electric vehicles act as power sources for the house or building they are plugged into. Similar to V2G, the battery pack will be charged again as the demand for electrical energy reduces. Smart charging systems can either be managed by the user or the supplier. User-managed charging gives customers the flexibility of choosing when to charge their vehicle based on their need and the price. On the other hand, supplier-managed charging is when the real-time energy production, state of charge information about EVs in proximity, and local energy consumption are all taken into consideration before electric vehicles in the area can be charged or discharged. Smart charging systems provide an interface for users and the system to work in synergy to maximize energy efficiency. When designing an electric vehicle, let alone any vehicle, safety comes first. But when it comes to the EV, there are concerns about the possibilities of electrocution, shock, and even explosions. These fears are often amplified by the instances of EV battery packs catching fire, which have obviously led to the safety of the electric vehicle coming under fire itself. So, let's take a look at how safe the electric vehicle actually is. Although the EV battery pack has a reputation for catching fire, IC engine cars are in fact more likely to do so because their fuel ignites much faster than the flammable lithium-ion electrolyte in an EV battery pack. If a battery pack sustains damage during a collision, a short circuit may occur and cause thermal runaway, which will overheat the electrolyte. If this is not controlled, the electrolyte will ignite and lead to an explosion. To make the EV battery pack safer, each individual cell is surrounded by advanced phase change materials that improve heat transfer as the material transitions from one phase to another. This also limits the risk of overheating in nearby cells. As the battery pack has many cells, the effects of the collision on one cell will spread like wildfire to the others. There's also a protective cooling shroud with coolant flowing inside it to prevent chances of damage or short-circuiting. EV battery packs are also subjected to testing under different conditions they may face to understand how they respond to each one. A few conditions under which they are tested include extreme temperatures, vibrations, overcharging, humidity, water, fire, and collisions. As the EV battery pack is equally distributed along the floor of the chassis and not mounted at the rear or front end, it is safe from direct impact in the case of a collision. Not only does this placement protect the battery pack from immediate impact, but it also lowers the center of gravity and provides more stability amidst collisions. This also reduces the likelihood of the vehicle rolling over upon impact. Electric vehicles also happen to be heavier because of their battery pack, because of which they experience less deceleration than lighter cars in the case of a collision. This puts passengers in the EV at a lower risk of injury when compared to those in cars that weigh less. There are also several partial offset crash blocks to keep the front wheels from hitting the battery pack in the case of a frontal collision. When sensors in the vehicle detect a collision, the EV has a system in place to isolate the battery pack from the rest of the vehicle's circuitry. This triggers special pyro fuses to disconnect the high-voltage electrical system from the system. However, to keep the hazard lights functioning, the 12-volt system will still continue to work. A major concern in EVs is the chance of shocks or electrocution. This brings many questions regarding their safety when in contact with water. However, electric vehicles are not fazed by water. The charging plug and socket are designed in such a way that water or dirt cannot penetrate them. Even more so, electricity only flows from the charging station to the onboard charger if there is no water in between the connections. If the charger does not happen to sense and come in contact with water, there will be no shock because the flow of electricity is immediately cut off. In the case of a thunderstorm with lightning, electric vehicles are designed in the same way conventional cars are, with a Faraday cage that keeps them safe from lightning. Apart from thunderstorms and rain, temperature fluctuations, whether hot or cold, are taken into consideration when it comes to safety. This is why EVs have a battery management system to monitor the temperature and status of the battery pack to keep it within safe operating temperature ranges. The BMS also has multiple temperature sensors that facilitate thermal protection. Electric vehicle safety considerations extend beyond just the passengers in the vehicle, as they also consider the safety of pedestrians around. Since EVs don't have an internal combustion engine, they produce much less noise. While most may consider this an added advantage, it in fact raises safety concerns because pedestrians may not be able to hear an approaching electric vehicle. In order to alert pedestrians of the EV's presence, noise emitters are installed at the front and rear ends of the vehicle to mimic the sound of an internal combustion engine. Countries have made it mandatory for such systems to be fitted in electric vehicles. Now, this just goes to show that safety goes the extra mile in electric vehicles and makes them just as safe as IC engine vehicles. Electromagnetic waves are everywhere. As a matter of fact, the electronic device which you are watching this video on, be it your mobile phone, laptop, or tablet, is sending out electromagnetic waves as we speak. On a larger scale, the vehicle you drive around, either an IC engine car or an electric vehicle, also generates electromagnetic waves. All of these systems have one thing in common. They are all combinations of electronic and electrical components, which are responsible for the emission of electromagnetic waves. When listening to music on your earphones, you've probably heard static sounds. This is caused by the interfering signals of the earphone and surrounding electronic systems. With all of these electromagnetic waves around us is a phenomenon called electromagnetic interference going on. This is when the electromagnetic waves within or external to an electronic system interferes with other electronics. If not managed, this can disrupt the normal operation of the electronic systems and can even become a safety hazard. And this is why electric vehicles are designed to be electromagnetically compatible. Electromagnetic compatibility, or EMC, is when an electronic system is able to function in an environment with other devices emitting electromagnetic waves. It will also not emit electromagnetic waves in ranges that affect the working of other devices in its surroundings. But where do the electromagnetic waves come from in electric vehicles? Electromagnetic waves in EVs originate from each electronic component, a few of which include the motor, motor controller, converter, battery pack, and an onboard charger. The primary source of these waves happens to be the power converter, electric motor, and battery pack, which all operate on high voltages. As a result of this, they emit electromagnetic waves of higher magnitude than other electronic components that operate on low voltages, like the headlights. All of these components are connected together by a high voltage and low voltage wiring harness. Placing these two wiring harness systems together in an EV also causes EMI due to the varying frequencies of electromagnetic waves that they emit. The switching of power semiconductor devices also helps in the control of motors. The switching action also causes EMI. All of these happen to be sources of EMI from within the EV. External sources of EMI for the EV include chargers at the charging station and wireless charging mechanisms. Electronic components within the vehicle make up different electronic systems like the suspension control, information navigation, headlights, and brake pressure systems. As each system emits electromagnetic waves, a good amount of interference goes on within the EV. If this interference is not managed and the EV is not electromagnetically capable, it may lead to malfunction or failure. For instance, the motor controller in an electric vehicle works on electromagnetic components like IC chips and sensors that emit an electromagnetic wave. If these components do not pass EMI and EMC compliances, they may cause a malfunction. To make sure this does not happen and the EV is safe for use on and off the roads, EMC testing is performed to determine if they are operating within safety standards. It is because of this that parts of an EV should have an EMC certificate. These certificates are given after the vehicle passes a series of tests for EMC based on standards set by organizations. The EMC of an EV is studied through laboratory and road tests, which assess the emissions, susceptibility, and immunity of the vehicle. Laboratory tests are performed to determine the electromagnetic wave emissions, as well as the susceptibility of each system in the vehicle to EMI. This test is performed in an EMC test chamber that is anechoic. By assessing the susceptibility of the vehicle, we can gauge how vulnerable the EV is to the other electromagnetic emissions. When testing this, the EV will be the only device in the room, and all other devices will be switched off to determine their magnetic wave. Outside tests are carried out to test the vehicle in real-world conditions. The vehicle will be driven in maximum acceleration and deceleration to identify the amount of current developed during traction. Leveled roads are used for this purpose because the magnetic wave of the Earth is relatively constant. When performing these tests, we can determine external sources of electromagnetic waves as well. Certain design considerations can be taken to maximize EMC and limit EMI in an EV. For instance, the motor in an EV can be fixed to the chassis to reduce the amount of electric potential as much as possible. In addition to this, motors and power cables need to be placed at a distance from the passenger seat area. Power cables in the vehicle can also be twisted and insulated to reduce their emission of electromagnetic waves that can interfere with other systems. So, electromagnetic waves are literally everywhere, and for all you know, your mobile phone could be interfering with the electromagnetic waves of an EV right now. Zero emission, non-polluting, and eco-friendly are just a few of the terms used to describe the electric vehicle. While this does hold true to a certain extent, the electric vehicle is unfortunately not 100% eco-friendly. It is still less harmful to the environment than the IC engine car, as one electric vehicle can save around 150,000 kilograms of carbon dioxide per year. Since all electric battery EVs only have a battery pack but no combustion engine, they emit no exhaust from their tailpipe. However, hybrid and plug-in hybrid EVs do have a combustion engine along with a battery pack, which results in exhaust emissions. But the amount of emissions from these vehicles is still 17 to 30% less than that from an IC engine car. So by shifting to electric vehicles, hybrid or all-electric, the overall tailpipe emissions of pollutants like oxides of carbon, nitrogen, and sulfur can be brought down. On top of reducing greenhouse gas emissions, electric vehicles also minimize the release of particulates like soot into the atmosphere. A road with just electric vehicles would have less soot emissions, which in turn reduces the impact it has on the respiratory health of living things. Unlike IC engine cars, the battery pack in EVs adds extra weight to their system. This leads to a rise in the wear of the tires, which contributes to particle pollution. Most EVs are, however, designed with special tires that can manage the heavy weight of batteries to reduce associated wear. While EVs might sound great when it comes to the lack of emission, the process of manufacturing an EV does have negative impacts on the environment. Here's a look at how the manufacturing process of electric vehicles, and specifically the battery pack used in them, affects the environment. Studies have suggested that manufacturing an EV generates more pollution when compared to the IC engine car due to the additional energy needed to make an EV battery pack. In fact, data suggests that there is 30 to 40% more greenhouse gas emission during the production phase, most of which is from the battery. What's more is that the factories manufacturing batteries used in electric vehicles often use energy from non-renewable resources. This is why many EV manufacturers have defined rules for battery suppliers to use only renewable energy sources when manufacturing it. Despite such measures, during the entire manufacturing cycle, from production to transportation, EV battery packs still require a lot of energy that accounts for more carbon emissions than the EV ever produces over the course of its lifetime. But before all this, rare earth metals like lithium, cobalt, nickel, copper, vanadium, and indium that make up the battery need to be obtained. The means by which this is done involves deep mining, which has severe impacts on the environment. At the moment, lithium is the most extensively used element in EV batteries. The process of extracting lithium from the ground consumes a lot of water and energy. The amount of each metal that goes into the making of each battery depends on the type of battery and vehicle model. To put this in perspective, an EV battery could have around 8 kilograms of lithium, 14 kilograms of cobalt, 20 kilograms of manganese, and 35 kilograms of nickel. When compared to IC engine cars, EVs require 6 times more minerals. So relying on these will definitely put immense pressure on land mineral ores, even if the dependence on fossil fuels reduces. This marks the need to identify alternative ways of powering EVs. As a good amount of the EV's cost is from the battery pack, increased prices due to the scarce resources would drive many consumers back to IC engine cars. While battery prices reduced by 50% between 2014 to 2018, the recent years have only seen a 10% reduction. If we look at the EV as a whole, the motor, charging system, and BMS require more integrated circuit chips. To manufacture these components takes millions of liters of purified water a day and leaves a significant carbon footprint. A rise in demand for minerals could further amplify the release of greenhouse gases and loss of biodiversity. Recycling batteries could prevent a lot of problems, but this is a complex process that contributes to global warming in itself. Although lead-acid batteries used in the automobile industry can be recycled with ease, the same does not apply for the lithium-ion battery pack. This is because they are bigger in size and weigh a lot more because of having thousands of lithium-ion cells. Safety also comes into question because they have hazardous materials and may even explode. Battery materials like lithium, cobalt, nickel, and manganese can be recycled. But the process of getting these metals is hard because the battery needs to be shredded and broken down with heat or chemicals from special facilities. Transporting the battery pack accounts for 40% of the cost because it is also a cumbersome process. At the moment, only around 5% of EV batteries are recycled. Nissan has taken initiative to recycle and reuse old batteries from the Leaf and use it in automated vehicles that transport parts and factories. Volkswagen has also opened their first recycling plant and intend to recycle 3,600 battery packs per year initially. By recycling EV batteries and their parts, overall environmental pollution associated with them can be reduced. Another source of greenhouse gas emissions happens to be the power grid that charge electric vehicles. Some charging stations receive energy derived from non-renewable sources like coal to generate electricity. Certain countries that use oil, coal, or natural gas for power to charge their vehicles may experience harsher environmental impact than others. The greenhouse gases resulting from this can be reduced by using renewable energy sources like wind and solar power for electricity. If we were to look at the overall efficiency of EVs and IC engine cars, the measure of well-to-wheel efficiency can be used. This is the measure of energy and emission associated with the transportation of fuel right from the time of production to their use in vehicles. For an electric vehicle, well-to-wheel efficiency is in terms of energy from the production of electricity, conversion, and transmission to the point where the battery charges the EVs. When comparing the two vehicles, an electric vehicle happens to be 2.5 times more efficient than a petrol-powered counterpart. So while EVs don't exactly bring greenhouse gas emission down to a zero, they do offer a much greater alternative for a much greener future. Maximizing the torque and efficiency of an electric vehicle is the goal of car manufacturers everywhere, and the key to doing this lies in the type of motor they use in their design. While each electric motor has a unique working that brings its own set of pros and cons, engineers focus on finding the configuration with minimal limitations and maximum efficiency. And this is exactly what Tesla did when it introduced the Internal Permanent Magnet Synchronous Reluctance Motor, or IPM Syn-RM motor for short. This motor has combined the permanent magnet motor and synchronous reluctance motor to reap the benefits and overcome limitations of permanent magnets and reluctance. Since its inception, Tesla has used it in their Model 3 EVs as well as the Model S and X. An added advantage of the IPM Syn-RM motor is that it is easier to cool than the induction motor. Before the introduction of this motor, Tesla was using the induction motor developed by Nikola Tesla. However, in the process of developing current in the rotor of the induction motor, an energy loss of up to 5% was observed. Although this may seem like a negligible amount, it is enough to significantly bring down the performance and functioning capacity of an electric vehicle. It is this very reason that drove Tesla to replace their induction motors with the IPM Syn-RM motor. Here's a look at how the permanent magnet motor and synchronous reluctance motor have been integrated in the development of the IPM Syn-RM motor. The permanent magnet motor induces a back EMF when the magnetic fields of the permanent magnets align with that of the stator windings. And when the speed of the motor increases, the amount of back EMF does as well. This basically gives a reverse voltage to the system and makes the permanent magnet motor less efficient in high-speed conditions. But by integrating the principle of reluctance to this motor, it can still be used in high-speed conditions. Let's look at how this works in a synchronous reluctance motor. Iron has low reluctance, because of which magnetic flux flows through it readily. Synchronous reluctance motors use this property to develop torque. The rotor has slots in it, which increases its state of reluctance. When the rotor rotates by 45 degrees, it shifts to a state of lower reluctance. As the rotor is inclined to seek a low reluctance state, the magnetic field will continue to rotate along with the rotor. This means that the rotor and magnetic field will always be in sync. The resultant torque from this is called reluctance torque. These motors do not give rise to back EMF and can function in high-speed conditions. As the permanent magnet motor can work efficiently in low-speed conditions, and the synchronous motor can work efficiently in high-speed conditions, combining the technology of the two can make sure they work efficiently across all speed ranges. The integration of these two motor configurations also avoids the issue of back EMF. By placing permanent magnets into slots of the iron core, back EMF can be avoided because the magnetic effects on the stator windings are minimized. This motor maximizes the torque output because it combines permanent magnet and reluctance torque. Tesla has engineered the motor to have an EMF angle of approximately 50 degrees at which the most torque is generated. In addition to Tesla, the IPM Syn-RM motor is also used in the Toyota Prius. But what sets the motor apart in the Tesla is the use of segmented magnets in the slots of the iron core to reduce eddy current losses. However, the Toyota Prius just has a solid magnet without segments, because of which it is more prone to overheating. By minimizing limitations, the IPM Syn-RM motor is on the way to optimizing the working of electric motors in the EV industry. Most of us have been anxious about whether the amount of fuel or charge left in our vehicle is enough to get us to our destination. This feeling actually has a name to it and is called range anxiety. It is driven by the fear of getting stranded in the middle of the road if there is no more juice left in the car. Range anxiety is more common among electric vehicle drivers due to the lack of charging infrastructure available in the case that their electric vehicle runs low on charge when on the go. It is to ease this anxiety that range extenders are used in EVs. But what is a range extender? A range extender is a setup with an auxiliary power unit based on fuel, mostly from an internal combustion engine, that charges the battery pack of the EV. The power source in the unit may vary depending on the generation of range extender used. The first generation has IC engines. The second generation has piston engines, and third generations have micro turbines and fuel cells. But the general setup with a small IC engine that powers the battery pack is more widely used. Range extended vehicles are also called series hybrid vehicles. In this case, the IC engine powers an electric generator and never directly drives the wheels of the car. Two main examples of range extended vehicles on the market include the Chevrolet Volt and BMW i3. Since most range-extended vehicles use conventional fuels, they can be refilled at fuel stations. This brings down range anxiety caused by the search for charging infrastructure. Here's a look at how range-extended EVs alternate between battery pack and IC engine power sources. The SOC of an EV battery pack is around 100%. As there is no need for the IC engine to step in at this point, the vehicle operates on battery mode. This means that the wheels are driven by the electric motor that is powered by the battery pack, which can also be recharged through regenerative braking. Since the IC engine fuel is not used here, there is no emission of greenhouse gases. It also oversees and controls the use of charging devices and the flow of electrical energy to maximize the efficiency of charging and energy consumption. It is important to note that even during certain periods in this mode, the IC engine will be off, and most of the load will be supplied by the battery pack. So the IC engine in range-extended EVs acts like a last resort, and is smaller because it only has to meet average power demands. The major power demands will still continue to be met by the battery pack. When the driver charges their vehicle again, it will return the SOC to around 100%. Even more so, the control system in range-extended vehicles uses all the charge it can before switching to the range-extending fuel. This makes this EV relatively more eco-friendly when compared to others that also have an IC engine powering them. While extended range EVs thrive on increased range from the IC engine, they do not have to bear the weight of the gearbox in IC engine vehicles. All of these features combined allow these vehicles to convert fossil fuels to electric power in a much more efficient manner. So, although range extenders are used to increase range, they extend into more than that and improve the overall efficiency of EVs. With technology advancing faster than ever, autonomous electric vehicles might be the next big thing in the automobile industry. Since electric vehicles are already redefining the automobile world, integrating autonomous features into them would take things one step further. Before we get into autonomous electric vehicles, let's take a look at autonomous vehicles. Autonomous vehicles are cars that are aware of their surroundings and can safely move around. They have in-vehicle data loggers that record data through the use of sonars, GPS, radars, LiDAR, odometry, and thermographic cameras. By logging data, the automated vehicle can respond according to the inputs and improve the performance of the system. Adjustments to the behavior of the vehicle may be done manually by the driver or automatically through artificial intelligence algorithms. Advanced control systems even use sensory information to determine whether there are obstacles on the way and the right path to take. These vehicles use artificial intelligence and combine hardware with software to develop safe autonomous features for drivers. The extent of human intervention required in these features can be classified under 6 different levels defined by the Society of Automotive Engineers. With each increasing level is the use of more autonomous features and technologies, and a reduction in the need for human intervention. They range from level 0 to level 5, with level 0 having no driver automation and requiring 100% manual control from the driver, and level 5 being fully automated with no need for manual inputs. The received inputs are used for autonomous features like lane control, adaptive cruise control, street sign recognition, object or collision avoidance, automatic emergency braking, and light detection and ranging. Other autonomous features include vehicle-to-vehicle communication, traffic jam assist, reverse parking assist, blind spot detection, and electronic stability control. At the moment, Level 3 and Level 4 automation are being tested on conventional and electric vehicles. In fact, Mercedes-Benz has obtained approval for its technology of Level 3 autonomous driving that receives inputs regarding traffic signs and events, the geometry of the road, and the route profile through the use of surround sensors. There are, however, no production vehicles with Level 3 and 4 automated features, as it is only available in test vehicles for the process of technology development. For both electric and conventional vehicles, only Level 2 software is currently available in the industry and provides partial automation that supports drivers when braking, steering, and accelerating. It also helps in adaptive cruise control, lane centering, and maintains distance between the car and others in front during stop-and-go traffic. But as this level is not fully automated, it still requires the attention of the driver to keep track of the vehicle's movements and intervene when needed. The driver is required to have their hands on the wheel and be ready throughout the ride. This level of automation in electric vehicles is seen in Tesla's Autopilot, along with that of the Mercedes-Benz Drive Pilot and Audi Traffic Jam Pilot. As electric vehicles have drive-by-wire systems and less moving parts in general, it is much simpler to integrate autonomous features into them. Electric vehicles can also operate the high-powered autonomous components and features better than IC engine cars can. What's more is that by implementing autonomous features that identify the optimal route, rerouting due to human errors in navigation can be avoided. This can improve range and reduce range anxiety among EV users. Integrating autonomous systems into vehicles also has the scope of bringing down the percentage of road accidents caused by human error. This is because around 94% of road accidents are attributed to human error. On top of this, greenhouse gas emission can also be brought down, as the autonomous electric vehicle would be able to monitor traffic in the area and avoid taking longer and unnecessary routes during travel. Autonomous electric vehicles also provide mobility for those who cannot operate a vehicle properly. While autonomous electric vehicles do open up a realm of possibilities, the addition of autonomous systems in electric vehicles will require more power. This will, in turn, increase the power demand in electric vehicles. To overcome this challenge, autonomous systems can be integrated in hybrid EVs so that there is less demand placed solely on the battery pack. In the case that the battery runs out, the IC engine will always be there to take over. All these features combined put autonomous electric vehicles at the forefront of the future of the automobile industry. Electric vehicles have come a long way and have significantly increased in number over the last decade. It is predicted that around 145 million electric vehicles will be driving on the roads by 2030. To make this happen, research in the automobile industry is currently making strides towards advancements in EV technology to fast-track their adoption. Let's take a look at some of the technology that is currently underway to make the EV the future of the automobile world. For electric vehicles, it has always been about finding the right type of battery pack that offers good range and capacity while coming at an affordable cost. At the moment, lithium-ion battery packs offer just that and are extensively used in the EV industry for their high energy density and affordability. But this does have a catch. The process of extracting minerals such as lithium, cobalt, and nickel from the ground has its own set of challenges and harms the environment through intense mining processes that take a lot of energy and water. As a matter of fact, electric vehicles can use 10,000 times more lithium than that used in smartphones. By 2040, the demand for lithium and nickel production is expected to increase by 40 times, and the demand for copper, cobalt, and graphite production is expected to be 20 times more than that in 2020. Seeing these numbers and the impact that obtaining these minerals has on the environment in terms of the mineral reserves, research into other battery technologies that use less of these minerals is ongoing. Although cobalt improves the energy density of lithium-ion batteries, it is toxic and poses a threat to living beings and the environment. There are about 14 kilograms of cobalt in a battery pack, and research is ongoing to determine whether cobalt-free electrodes or low-cobalt materials can be used. Even though nickel is not expensive like cobalt, researchers want to cut down on its use as well. This will demand the switch to materials such as crystal structures called disordered rock salts that are composed of vanadium, lithium, and oxygen. As their name suggests, these are salts with an unordered structure. Disordered rock salts bring scope for a new anode material. Unlike other materials used in battery packs, these rock salts do not need nickel or cobalt to stay stable and can be made with manganese instead. This provides a safe alternative that does not take a significant toll on energy density. Another area of research in electric vehicle battery technology is that of solid-state batteries. Research into solid-state batteries for electric vehicles shows that they will offer twice the amount of energy density and a higher power-to-weight ratio, as the pack will no longer have fluid electrolytes. This means that they can offer more energy for the same weight as the lithium-ion battery pack with fluid electrolyte. When it comes to electric vehicles, this is a major advantage as more energy density improves range. Battery pack still uses lithium. Scientists have developed a solid-state battery with silicon. By replacing the anode with silicon, it can be charged across a range of temperatures. Unlike battery packs that use a lithium anode that have requirements to be charged under specific conditions, this will in turn increase the rate of charge at normal temperature ranges while providing higher energy densities. It also poses less harm to the environment, is cheaper, and safer to use. Research in Sweden on structural batteries as a possible alternative shows scope for weight reduction of the overall vehicle. As weight reduces, the power needed to move it also reduces and increases range. It has even shown to increase capacity by 20% when compared to the lithium-ion battery. To top it all off, Tesla has even introduced this concept by suggesting that the entire battery pack can be built into the structure of the vehicle to solidify the platform. This brings down the mass of the vehicle by around 10%, and as less energy is taken to move the vehicle, it improves range by around 14%. What's more is that Mercedes-Benz is currently in the process of developing organic batteries with graphene, water-based electrolyte, and organic cell chemistries. But research into this is still in its infancy, just like that into solid-state and structural batteries. It may take a decade or two for these battery technologies to be tested and mass-produced. A primary barrier in the purchase of electric vehicles is their hefty price tag. As most of their price is accounted for by the battery pack, the future of the EV industry has a specific focus on reducing battery pack prices while ensuring optimal energy density, efficiency, and range with minimal impacts on the environment. If the plan is to accelerate the number of EVs on the road, it also means that there will be more EV batteries needing to be charged. This demands an increase in charging infrastructure. Over the last decade, charging infrastructure has seen an exponential growth in numbers. However, EV drivers and those wanting to purchase them may still experience range anxiety. To combat this fear, more charging stations will need to be set up. Developments in the field of charging infrastructure for EVs are finding more ways to provide drivers with flexibility. For instance, mobile charging units are being developed. This charging technology will offer a portable or temporary charging station that can be set up for use when on the go. They are powered by integrated batteries and do not require high investments in infrastructure. In addition to this is the development of wireless charging. Just like phones and other electronic devices, the future of EV charging may also be wireless. Inductive charging is one such method that makes charging wireless and requires the additional integration of two coils, where one coil will be under the vehicle and the other will be under the ground designated for charging. Parking lots, garages, and even roads that we drive on have the potential to be converted to EV wireless charging ports. Taking this a step further is dynamic charging, which charges electric vehicles when they are on the go. All drivers have to do is drive on top of a lane designated for wireless charging with inductive coils underneath. This curbs the need of having to stop at charging stations and provides a way to increase range. While charging infrastructure develops, there is also a focus on reducing the time it takes to charge an EV. Unlike IC engine cars that just need a few minutes to be refueled, EVs take much longer. Although ultra-fast charging mechanisms are currently available, they are scarce and not sufficient for the entire population. This requires more ultra-fast charging infrastructure for all people to access. So, most power chargers in the future are intended to provide more power in a single charge to bring down charging time to just 10 to 15 minutes. In fact, Australia has already started work on developing a nationwide ultra-fast charging network for electric vehicles. By doing this, drivers can drive across the country without range anxiety and charge their vehicles in just a matter of minutes at charging points. On top of ultra-fast charging is the development of battery technology that can expedite charging speeds. But as charging infrastructure develops, so will the need to increase the power available from power grids. High demands in power will need to be met as the number of EVs increases. Moreover, the source of electricity should be from renewable sources that do not contribute to global warming. This is why vehicle-to-grid charging, which in other words is bidirectional charging, is being looked into. When vehicle-to-grid charging is enabled, energy from the battery pack of the electric vehicle can be used as a power source to power systems they are connected to. This would be useful during periods of peak load on the power grid or power outages. Advancements in EV technology don't stop with just battery technology and their source of power. The future of electric vehicles may also involve the integration of autonomous features. Autonomous electric vehicles integrate autonomous and electric features and have the potential to bring down the large number of road accidents caused by human errors each year. Since these vehicles have systems that provide an overview of traffic in the area, autonomous EV use can reduce traffic congestion and determine traffic movements in and around them. By doing so, they reduce the inconvenience, dangers, and environmental impacts caused by traffic. If ride-sharing vehicles are autonomous electric vehicles, the number of miles traveled and greenhouse gas emissions can also be reduced. The amount of IC engine vehicle distance traveled can be reduced by decreasing the use of private IC engine cars and increasing the use of shared mobility, which lets travelers commute together. Fast-tracking the release of more electric vehicles on the market also requires manufacturers to scale up their production rates. The future of EVs requires getting the concept of a car and producing it in large volumes to meet high demand in EVs, which will in turn reduce the price of electric vehicles. With all of these advancements set in motion, electric vehicles are definitely on the road to electrifying the world. When you pull the brakes and come to a sudden stop on the road, you may have felt the front of the car dip forward. If it weren't for the suspension system, this dip would be way more out of control. On top of this, if cars didn't have suspension systems, bumpy rides and rigid turns would all be very common. In any car, electric or conventional, the suspension system works to keep the car in control and provide a smooth driving experience. Let's take a look at how this is done. Suspension systems increase the friction between tires and the surface of the road in order to ensure good handling, control, and stability of the vehicle. They absorb shock energy from bumps on the road and support the weight of the vehicle to maximize comfort for passengers. It also has a role in the stability of the vehicle when accelerating, braking, and turning corners. In fact, it improves road isolation, cornering, and road holding. When you drive over a bump on the road, the suspension system absorbs the energy and dissipates it without letting the vibrations continue to the passenger compartment. This demonstrates road isolation, which is how well the car isolates the shock experienced from being felt by the passengers. But the suspension system does more than just keep the car under control when driving over a bump. When you turn a corner, the suspension system shifts weight in a controlled manner from the side outside the turn to the inside, making the turn. This makes cornering, which is just the ability of a car to turn on a curved path, much smoother and controlled. And similarly, when you pull the brakes or accelerate, there is a shift in weight to the ends of the vehicle. When braking, the weight shifts to the front of the vehicle and causes a dip, called a dive. And when accelerating, the weight shifts to the back of the vehicle and causes a squat. As the transfer of weight to either side of the car limits the grip that tire has on the road, the suspension system works to reduce and control this. To understand the mechanism behind the suspension system and how it does this, we need to go back to Newton's laws of motion that states that forces have a direction and a magnitude. For instance, when your vehicle drives over a bump on the road, the wheels will move up and down because it experiences a vertical acceleration. If there was no suspension system, the vehicle would momentarily lose contact with the surface and then come back down with an impact. But by absorbing energy from the bump, the suspension system makes sure this doesn't happen. This keeps the vehicle in contact with the ground at all times to prevent it from coming back down with an impact. The suspension system has parts that connect the vehicle to the wheels in the chassis. These parts include springs, shock absorbers, also known as dampers, and sway bars. Here's a look at the parts of the suspension system in action when the car drives over a bump. As the front wheels drive over a bump, the energy from the shock gets transferred to the springs of the suspension system. The springs absorb the shock and minimize the amount transferred to the body of the car. While there are different types of springs, the coil spring happens to be the most widely used. It makes up the assembly of the strut along with the shock absorber. Just like its name implies, a coil spring looks and behaves like a coil. This means that they compress and expand when absorbing shock from the wheel's motions. The mass that the spring supports above it is called sprung mass, and the mass that is connected to the bottom of the suspension is called unsprung mass. The way the sprung mass responds to the motion of the car is determined by how stiff the springs are. If the springs in the suspension are soft, like those in luxury cars, the ride will be smooth with minimal bumps because the suspension will absorb the shock. But it will still be vulnerable to diving and squatting when the car brakes and accelerates, and body roll or sway when the car turns corners. On the other hand, if the suspension is stiff, like those in sports cars, dive and squat are less, along with a reduction in body roll when cornering. However, it will not be able to absorb shocks from bumps to the extent that soft suspensions can, because of which they may make for a bumpy ride. If springs were the only way energy could be absorbed, it would be released in an uncontrolled manner, which would cause it to bounce until the energy fully dissipates. This is because although springs are good at absorbing energy, they are quite the opposite when it comes to dissipating that energy properly. This is why shock absorbers are used in the system to handle unwanted motion from the spring through a process called damping. They reduce the amount of energy from the vibrations of the spring. This is done by converting the kinetic energy from the vibrations to heat energy that can be released via hydraulic fluid. Shock absorbers have an upper and lower mount, where the upper mount is attached to the frame and the lower mount is attached to the front or rear axle. This part is velocity sensitive, so when the suspension moves fast, the shock absorber dampens the force more. So as the spring compresses and expands, the energy gets transferred to the shock absorber via the upper mount. It then travels down the piston rod and into the piston. As the piston moves up and down, fluid passes into it, which in turn absorbs the energy and slows the spring down. There are two cycles in the working of a shock absorber: the compression and extension cycle. When the piston moves down, the compression cycle takes place and compresses the hydraulic fluid under the piston. As the piston moves up, the extension cycle takes place and compresses the fluid above the piston. In addition to these parts is the sway bar that extends across the length of the axle and joins both sides of the suspension. They are used to provide more stability to the vehicle, specifically during turns. So when the suspension on one wheel moves during a turn, the sway bar translates this motion to the other wheel in order to ensure a balanced ride. This same process happens when the rear wheels also drive over the bump. However, the suspension system for the rear wheels is not the same as the one for the front wheels. Even when a car is not moving, the weight distribution across it is not even. And when the car accelerates or brakes, there is an uneven distribution of weight at the front and rear ends. This is why there are front and rear suspension systems. Front wheel suspensions are relatively more complex as they move along with the frame of the car and turn different angles as they are steered. A vehicle's suspension also has to do with the alignment of its wheels. In order for the wheels to be properly aligned, the angle of the tires needs to be adjusted. This in turn affects the way the tires make contact with the surface of the road. When it comes to aligning the wheels, there are three main aspects focused on. These include the camber, caster, and toe of the wheels. Here's a look at each one. When a wheel is viewed from the front, there may be an inward or outward tilt to the top of the wheel. This is called the camber angle. When the top of the wheel tilts inward, it has a negative camber, and when the top of the wheel tilts outward, it has a positive camber. Most wheels have a certain amount of negative camber as it is needed for good handling. On the other hand, positive camber is used in conditions that have heavy load applications, as it maximizes the contact between tires and surface of the road. If the camber is well aligned, it will maximize directional stability and road isolation in vehicles. Next is the caster of the wheel. For this, we look at the wheel from the side angle. The caster angle is the tilt of the steering axis forward or backward when viewed relative to a vertical line. When the top of the steering axis tilts backward, it is a positive caster, and when the top of the steering axis tilts forward, it is a negative caster. Caster is essential in enhancing the returnability of steering wheels and directional stability. And then there's the toe alignment. When considering the toe alignment, the wheels of the car are viewed from a top angle. The toe is the difference in distance between the back of the wheels and the front of the wheels. If the front of the wheels are closer together, it is known as toe in, and when the back of the wheels are closer together, it is known as toe out. There is zero toe when the wheels are parallel to each other. Wheel alignment is crucial in curbing the stress on the suspension system and avoiding rigid rides. It's important to have regular maintenance checks done on the wheel alignment and suspension system of cars because they are needed for as long as roads will have imperfections. All cars have a suspension system to ensure control and stability of the vehicle. But these complex systems are not all the same. Different suspension systems are used for different applications. There are three main types of suspension systems: independent, dependent, and semi-independent. Here's a look at how each one works. Independent suspension systems let the wheels move in a way that their movement does not affect that of the others. The wheels, therefore, act independent of each other as the wheels are not connected by a rear or front solid axle. A few common independent suspension systems include the McPherson strut, double wishbone, multi-link, trailing arm, and swing axle suspension systems. The most extensively used suspension system is the McPherson struts. It absorbs shock with a coil spring and shock absorber that have one end connected to the wheel hub and the other to the body of the car. While the spring absorbs energy along the ride, the shock absorber dissipates this energy as heat with the help of hydraulic fluid. Next is the double wishbone suspension system that has two control arms shaped like a wishbone. Each wishbone is connected to the chassis and is attached to the joint by a knuckle. In order to manage vertical movement, shock absorbers and coil springs connect to the wishbones. The two control arms are not the same size in order to prevent positive camber. This suspension system is commonly used in the rear end of vehicles and is mostly found in luxury cars. The multi-link rear suspension system has a series of lateral and longitudinal arms. There are generally 3 or more lateral arms and more than one longitudinal arm. These arms are not always equal in length. One end of these arms is connected to the wheel hub and the other to the chassis. As there are more arms, they provide more flexibility and let the vehicle handle different ranges of angles when driving. This suspension system is commonly used in off-road driving vehicles. The trailing and semi-trailing arm suspension have control arms that are connected to the chassis and axle of the car. It can control horizontal and forward motions, but not lateral motions. The control arms absorb forces from braking and manage the car during squat and lift. The swing axle is an independent rear suspension system that has an axle with the ability to pivot along the middle of its axis at the point connected to the U-joint. Unlike the independent suspension system, the dependent suspension system has wheels that move based on the movement of other wheels. So, if one wheel moves a certain way, it will influence the way the other wheels move as well. This suspension system has a solid axle at the rear and front ends of the car that connects the wheels together. Dependent suspension systems are mostly used in trucks or vehicles that carry heavy loads. Having the solid axle run along the transverse axis of the car lets it support and withstand the heavy load of weight, as the entire weight of the vehicle's body is held on the suspension. There are two main types of solid axle suspensions used in vehicles today: the leaf spring suspension and the panhard rod. The leaf spring suspension system has a series of metal plates stacked on top of each other, held together by a rebound clip. Each successive plate gets shorter in size, with the longest one known as the master leaf and the other ones called the graduated leaves. The leaf spring is connected to the solid axle on both ends. They are positioned parallel to the surface of the road to ensure optimal support of weight. However, the leaf spring suspension can only handle vertical movements. The panhard rod is basically a bar that is connected along the axle. It extends across both ends of the chassis. This suspension is preferred because it can control lateral motions. There are pivots on both ends of the suspension system that allow vertical movements. In between both independent and dependent suspension systems is the semi-independent suspension system, which lets wheels work on their own, but depend on the movement of others to a certain extent. The most commonly used semi-independent suspension system is the torsion beam suspension. It extends across the chassis of the vehicle and is attached to a trailing arm. It has an H-shaped structure that twists with each vertical movement from the trailing arms. While there are different types of suspension, they all have the common goal of ensuring stability, control, and safe handling of the vehicle. Getting behind the wheel and steering a car is an effortless task for most people. You turn the steering wheel, which turns the wheels. And although this sounds simple, there's a lot more to it. In fact, there's an entire steering system in cars dedicated to just steering it. By working together with the suspension system, the steering system provides drivers the control and stability they need over the vehicle for a safe driving experience. Let's take a look at what the steering system is and how it works. In any car, the steering system has a set of parts and linkages working together to translate driver inputs from the steering wheel to the wheels themselves. Now, if the steering wheel and steering linkages were directly connected, it would be hard to move the wheels. This is why a steering gear is in place to convert the rotational motion of the steering wheel into linear motion that turns the wheels. While there are different types of steering gears, the rack and pinion steering gear is the most widely used in cars. Here's a look at how it works. To turn a corner on a road, you turn the steering wheel according to how much you want to turn. What you don't see is that the steering wheel is connected to a steering column. As you can see here, a universal joint connects the steering column to the steering shaft and changes the angles between the two. The steering shaft is connected to the steering gear that has the pinion and rack setup. So a turn in the steering shaft will turn the pinion gear. As the teeth of the pinion gear move over the teeth of the rack, it moves the rack side to side. Over here, you can see that the pinion has a circular motion, and as it moves over the teeth of the rack, it makes it move linearly. This is what moves the rack side to side. At the end of the rack are the tie rods on both sides that allow rotational and translational motion. These tie rods are connected to the steering knuckles that connect to the wheels. It allows rotational motion and is connected to the frame of the car with a roller bearing to make sure that the wheels can only turn. There are steering linkages that join the steering gear to the wheels at the front of the car. These linkages have a specific geometric arrangement that is designed to prevent slipping. It is called the Ackermann steering mechanism that turns all four wheels in different angles to ensure that the car does not slip. To understand how it works, we need to know the basics of the wheel. There are two motions that a wheel experiences: rotational and translational motion. Rotational motion refers to the way the wheels rotate along its axis, and translational motion refers to the direction that it is traveling in. As you can see here, rotational motion and translation motion work in opposite directions and are supposed to cancel each other out to ensure that the velocity of the wheel at the contact point is zero. Only if there is no velocity at the contact point will the car be safe from slipping. If they do not cancel each other out, it is likely that the car will skid. The car is also prone to slipping if all the wheels turn in the same angle, because it would not result in perfect steering. To prevent the car from slipping, it should rotate about a particular center point, and this is exactly what the Ackermann steering geometry does. It ensures that all tires rotate about an imaginary central point for perfect steering, and that each tire follows a path with a different radius and rotates at different speeds. When the rack moves, the wheels on both ends of the car turn at different angles, because each wheel follows the radius of a different circle. Since the inside wheel follows a circle with a smaller radius, it turns more than the outside wheel. The angle between the wheels and the line connecting them to the central point is always 90 degrees. Front tires tend to move faster than rear tires, and depending on the turn made, the inside or outside tires move at different speeds. For instance, when making a right-hand turn, the wheels on the left side rotate faster because they have a larger radius circle to trace. In order for the steering wheel to move the rack from one end to the other, it takes around 3 to 4 full revolutions for the average car and 1.5 turns for race cars. This is because of differences in steering ratios. The steering ratio is the ratio of the angle of how much the steering wheel is turned to the angle of how much the wheels actually turn. For instance, if you turn the steering wheel by 180 degrees, and this turns the wheels by just 5 degrees, the steering ratio would be 180 to 5, or 36 to 1. The higher the steering ratio, the more the steering wheel needs to be rotated with less effort to rotate the wheels, and vice versa. The average car have a high steering ratio, making it easier to turn the wheels. However, race cars have a low steering ratio in order to increase responsiveness to steering input. This makes the steering wheel harder to turn. In any case, it is hard to turn the rack and pinion steering system without assistance. This is why power steering mechanisms are introduced in most cars today. It comes in 3 different types: electric power steering, hydraulic power steering, and electro-hydraulic steering. Here's a quick overview of each one. When electric power steering is used, there is a brushless DC motor used to drive the inputs from the steering wheel to the steering shaft and pinion. As the motor can rotate clockwise and anti-clockwise, it is capable of turning the rack to either side. The amount of power the motor should deliver to the steering shaft is determined by the electronic control unit based on inputs such as the amount of torque the driver applies to the steering wheel, the steering angle, as well as steering speed. Since the entire system has assistance from a motor, steering wheel rotation becomes much easier for the driver. Next up is the hydraulic power steering system that is only used when the driver is exerting a torque on the steering wheel. This is when a turn is about to be made and not when the car is driving in a straight line. Hydraulics take the torque input from the steering wheel by the driver and multiply it for the wheels. In cars with hydraulic power steering, it is much harder to turn the steering wheel when the car is off, but the moment the car is turned on, the steering wheel loosens up and is much easier to turn. This is because the hydraulic power steering system is powered by the engine through a belt and pulley. As the driver rotates the steering wheel, the vane also spins and brings in fluid at a low pressure and forces it out at a much higher pressure. This action of pressure is what eases the force having to be applied by the driver to rotate the wheel. The amount of torque given to the steering system is sensed by the rotary valve, aided by the torsion bar. As the top of the torsion bar is attached to the steering wheel and the bottom is attached to the pinion gear, it rotates upon application of torque from the driver. The electro-hydraulic power system is pretty much the same as the hydraulic system, but instead of getting hydraulic pressure from the engine, it gets its power to facilitate rotation from an electric motor. While steering may be effortless for the driver, you now know there is so much more that goes on than what meets the eye.